and then we'll share that out. What we did for the spring meeting was we put the recordings on YouTube, and then with the agenda, I could put the timestamps in for where the presentation started each day to make them easy to find, and especially for yesterday because we had a few folks that weren't able to get into the block 1 sessions. I'd really like to make those recordings available to folks. For the speaker guidance, I think most of the slots are 15 minutes. There are a couple that are 20 minutes. I guess just the first presentation by Monique Kuglitz, Dr. Kuglitz from Germany, and so she has a 20-minute block, and then the rest of them, I believe, today are 15 minutes. We will be doing a demonstration on this during the second break of the day with Dave Jones on GeoCollaborate. Okay, Vince, did you have anything else you wanted to add? Anything I left out?
Not really, not that I can think of. Maybe a quick summary that we did late yesterday afternoon, and I'll repeat it this morning. For those of you that are participating today as your first day of the meeting, reminder that the opening session yesterday, we had briefings from the various federal and partner agencies on their directions forward with well and fire research and applications efforts using Earth observation systems and tools, including from the U.S. Forest Service Fire and Aviation Lead. We also brought up the reintroduction or the new introduction of the NASA Well and Fire Initiative from NASA Earth Science Division and Earth Science Division Applied Sciences Program to be started up this fiscal year, and part of that in the ESD wildfire program to be started up in FY23. So that's an exciting new initiative that'll be starting and provide sources for us for exchanging further information on the use of Earth observation data through program solicitations and collaborations with our partners in the community. We heard about the US Geo, US GCRP, and the ICAM's rapid fire EO assessment. We had a perspective from the Office of Management and Budget from Grace Hu and Mark Hazelgren, and we had Paul Stebline brief us on the well and fire strategic plan for DOI, and then we continued on with summaries on the fire season from Tom Mellon, and then a kind of refresh on the NASA Aeronautics Research Mission Directorate, ARMD, on the wildfire management workshop that they had held in conjunction with our TFRSAC in the spring. And PK did a report out on the next steps and the results of that workshop and where we're going in the future. Win Idle provided an update on the thermal working group, and Josh Johnson and Alan Catton provided updates on the Canadian Torchlight update and on Torchlight update and on the Canadian FireSat system. And then Adam Watts, of course, provided an update on the FASME efforts and what's coming up for this coming year in 2022 with FASME. And then, of course, as Everett said, we started out in the afternoon with the first of our AI ML, artificial intelligence machine learning blocks of presentations. And this morning, as Everett just mentioned, we're continuing on in that theme with the next series of 2 blocks that cover AI. And with that, Everett, I'll let you introduce our first speaker.
Okay, Monique, if you want to unmute your phone, and there you go. I'll go ahead and advance the slides for you. Monique is, she joins us from Berlin. She's the innovation manager at Fraunhofer HHI and the chair of the ITU WMO UNEP focus group for AI for natural disaster management. And I really felt like her background and her work that she's doing was the perfect kickoff for today's meeting. Anything else you'd like to have as a preamble before we get started, Monique?
No, that's fantastic. Thank you so much for the introduction, and it would be wonderful, yeah, if you could move the slides as we go through this. So, yeah, it's a pleasure to be here at day 2 of the Tactical Fire Remote Sensing Advisory Committee meeting. I'm really looking forward to giving some insight on the focus group and to encourage your participation. So, if you don't mind jumping to the next slide. Thank you. Natural disasters are damaging physical events of predominantly natural origins. So they can be atmospheric, hydrologic, geophysical, oceanographic, or biologic. And impacts of these events can include injury, mortality, displacements, damage to property, including cultural heritage and infrastructure, and disturbance to nature and natural resources. In fact, a recent report from UNDRR, the Center for Research and Epidemiology of Disasters, IRSS, and UC Louvain shows that the 389 natural disasters that occurred in 2020, excluding biological disasters, impacted 98.4 million people, caused 15,000 deaths, and cost $171 billion US. Unfortunately, the impacts of these events are exacerbated in certain regions, such as small island developing states and least developed countries, and for certain populations, such as women and children. And they're also expected to worsen because of population growth, urban development, and a growing frequency and intensity of some events. Next slide, please. Thanks. So consequently, natural disasters are addressed in the activities of many UN organizations and programs, including the SDGs and policy guiding publications such as the Sendai Framework. For instance, I assume that everyone here is familiar with SDG 13, which is a call for action to limit climate change and its impacts. But I hope that we're also familiar with SDG 11, which looks at approaches to disaster risk reduction. And I also hope that we consider the other SDGs who are impacted. For instance, SDG 3, which is dedicated to good health and well-being, or SDG 1, which is dedicated to eradication of poverty. So I hope that the implications of these events are not underestimated. Next slide, please. Now, through advances in AI-based algorithms, a growth in computational power, and the emergence of large and often publicly available data sets, there's been an increase in the use of data and AI-driven approaches to solve tasks in many scientific fields, including health or fintech. And this raises some questions. Through tapping the potential of AI, can we improve our understanding of natural hazards, such as wildfires, our ability to detect events in real time, our ability to forecast events, and our ability to effectively communicate in an impending or ongoing disaster? What are the best practices when using AI, and what are the limitations? So as you can see in this figure on the bottom right, which was published in the February issue of EOS, some priority areas include creating documentation with standards and repositories to facilitate sharing and discovery, generating new benchmarks, and developing architectures and frameworks catered to the needs of geospatial data. Next slide, please. So we're exploring best practices in data-related processes to support the training and testing of AI-based algorithms, how AI-based algorithms can be used to detect and forecast events, and how AI-based algorithms can contribute to effective communication. So let's have a look at these categories in a bit more detail. If you could go to the next slide, please. Thanks. High-quality data are the foundation of AI-based algorithms. So some questions to explore are, what requirements should data meet when being used to train or test an algorithm? For instance, what are the best practices when it comes to data collection and storage, data quality and pre-processing? What do we expect when it comes to spatiotemporal resolution and the extent of our data? And how about the representativeness of our data? Can AI-based algorithms be used to enhance our data quantity? Using AI-based algorithms, can we detect changes in landscape features in time and create data sets that reflect those changes? For instance, changes in burn areas. And through methods such as federated learning, can we avoid data export issues? So for certain hazards, such as tsunamis, we've discovered within our focus group that you can use things like federated learning to avoid data export issues when certain countries do not want to share their data. And can AI-based algorithms be used to enhance data quality? For instance, can they help us to locate inhomogeneities in a data set? Next slide, please. Thanks. AI-based algorithms can be used to enhance and improve the traditional models used to develop numerical-based forecasts and physics or data-driven projections of natural disasters. They can also be used to detect features in real-time data streams and support early warning systems. So some questions we want to explore are, what is the current gold standard method to detect or forecast an event? And how can an AI-based algorithm bring this method to the next level? How can AI-based algorithms be used to leverage synergies from different data sources more effectively? Can they help us identify complex relationships and patterns in data? And what should be considered when we evaluate an AI-based algorithm? And in this graphic, a statistical dynamical hurricane forecast model from the National Hurricane Center is being compared with a grid-based recurrent neural network. Next slide, please. The Sendai framework advises us to develop, maintain, and strengthen people-centered, multi-hazard, multi-sectoral forecasting and early warning systems, disaster risk and emergency communications mechanisms, social technologies, and hazard monitoring telecommunication systems. So some of the questions that we're exploring are, once a natural disaster has been detected or forecast, how can AI assist with the immediate response? For instance, through an early warning system, push messages to cell phones, automated translation services, decision support systems, chatbots, or dashboards. And how do we ensure that communications methods are reliable and trusted by the population? Are they accompanied by a clear set of protocols to ensure that individuals know how to respond? Next slide, please. Thanks. So these topics are being explored and used to produce a series of deliverables. We're holding workshops that bring together experts and stakeholders, that highlight groundbreaking activities in this domain, and that encourage participation in our other focus group activities. So please note that our next workshop is scheduled for the 16th of March, and everyone is welcome to participate. The roadmap, which we are creating, is going to be a database of activities related to pre-standardization or standardization in the use of AI for natural disaster management. And it'll help us to create a gap analysis. We're also making a glossary of common technical terms and definitions to ensure that experts in different fields are speaking the same language. Given that we have so many people involved in this focus group from different fields, we've detected some differences in how we use certain expressions. So we're trying to come up with a way that we can facilitate communication and avoid confusion. We're also producing non-normative technical reports that summarize the findings of our analyses based on input from selected use cases. So here I just want to mention that we have an open call for use case proposals. So if someone who's listening to this has a use case that's using AI to detect, forecast, or assist with the communication of wildfires, I hope you'll consider submitting a use case proposal so that we can explore your approach in our report. And we're also making educational materials to make the content of the technical reports accessible to all stakeholders and to support capacity building. Next slide, please. So to do this, we're building a community of experts and stakeholders. Now, our focus group is based at the International Telecommunications Union. This is the UN body which is responsible for information and communications technologies, and it's a standard developing organization. ITU focus groups support the efforts of an associated ITU study group. So, for instance, the mandate of the parent study group for the focus group includes telecommunications for disaster relief, early warning, network resilience, and recovery. The focus groups provide a working environment for pre-standardization or standardization activities in a chosen area. So our area obviously is AI for natural disaster management, but there are other focus groups that are looking at things like AI for health or AI for autonomous driving. And these focus groups can be rapidly established and have the freedom to choose working methods, leadership, financing, and their desired outputs. So the deliverables that you saw on the last slide. Next slide, please. So our focus group brings the ICT and standardization expertise of the ITU with the natural disaster expertise from the WMO and UN environment to provide a platform for international, multi-stakeholder, and interdisciplinary collaboration on this topic. Next slide, please. So the focus group has a multi-tiered structure. So as you can see on the bottom left, we have these colored tiles. These show our topic groups. The topic groups represent clusters of experts who are exploring how AI is being used for a specific application, so detection, forecasting, hazard mapping, and for a specific natural hazard. So for instance, we have a group looking at tsunamis. I have a yellow arrow pointing at our group that's looking at monitoring and detection of wildfires. So you're welcome to have a look at those types of topic groups that we're looking at. Above those, we have a row of gray tiles. The first 3 represent our working groups, which are dedicated to drafting the 3 technical reports. So they digest the output of the topic groups, they survey the body of literature, and they connect with experts to look at how is AI being used in the field, what are the best practices, and what are the challenges when using AI. So they are exploring best practices when it comes to data. So this working group has been co-chaired by Arif Albayrak from NASA headquarters and Alison Craddock from NASA JPL. The second one is looking at modeling. This is being co-chaired by Jackie Ma from Fraunhofer Heinrich Hertz Institute and Andrea Toretti from the European Commission's Joint Research Center. And the third working group is looking at communications technologies. And this is co-chaired by Ivanka Pelivan from Fraunhofer Heinrich Hertz Institute and Tom Ward from IBM. The fourth working group is dedicated to building the roadmap, this database that I mentioned earlier, and it's being chaired by David Ullman from UNFCCC. And one of our most recent additions to our activities is a work stream, which is looking at tools, including online platforms, that can support the use of AI for natural disaster management. Our colleagues at the ITU TSP Secretariat, Maitili Manon and Hiba Tahawi, keep the focus group on track and support the management team. And if you go to the next slide, then you'll see who we are. Thanks. So supporting me is Elena Shoplaki, who's a climate scientist at the University of Gießen. Jörg Luderbacher is the Director of Science and Innovation and the Chief Scientist of the WMO. Moralitha Marukudi is the Operations Manager at the Crisis Management Branch at UN Environment. Srinivas Chaganti is from the Department of Telecommunications in India. Rukia Babamaji is from the National Space Research and Development Agency in Nigeria, and also part of the African Union's AFSTAG DRR group. And Yan Xuan Wang is from China Telecom. Next slide, please. Can we go to the next? Thank you. So this is actually my favorite slide. It's how you can get involved. So first of all, I invite you to visit our website. There you'll find all the information that I just provided and also more information. I encourage you to peruse our onboarding document that will show you how you can create a free ITU user account. It will show you how you can join our mailing list. That's where we provide information about our upcoming events or calls for proposals. This will also help you to register for our workshops and meetings. As I mentioned, on the 16th of March, we have our next workshop. We also have a meeting the 26th to 28th of January. So again, if there's anyone who's watching this who's interested in proposing a use case to be included in our activities, that would be the opportunity. 26th to 28th of January, that's when we'll be receiving and discussing these use cases. The website will also give you information on how to use our remote participation platform, how to access our collaboration site. That's where we have all of our documents in their various stages of development. And it's also where you can submit any written contributions. So I thank you very much for your time. As Everett mentioned, I believe that my email address will be available later on. So if anyone has any questions about the focus group or an interest in participating in any way, I encourage you to reach out. So thank you very much.
Well, thanks so much, Monique. And I guess at this point, I would open it up to any questions from the audience. Anyone that would like to speak, you'll need to unmute your phone. I've been muting people as they've been coming online to keep the background noise down. But if you would like to, or you can raise a hand and post it in the chat window, however you want to do it. We're a little bit ahead of schedule, which is great. But yeah, I thought this was exactly what I was looking for our kickoff presentation this second day here. And I think that being able to get actively involved with the work that you're doing through these different working groups. I think that's a good opportunity for us as we're looking to work our way into some of these capabilities that'll help us do a better job of processing our data, analyzing data, producing products, and so forth. So that's sort of my focus.
Wonderful, wonderful. Well, I do think that because there are so many use cases that are coming together and also people from different fields coming together, there is an opportunity to really learn and explore methods being used for other applications and to test them. So I think it's sort of a mutually beneficial situation that we're in the focus group.
Right.
Edward, you might read off Dave Jones' comment in the meeting chat.
Okay, let me pull that up. Let's see. Dave Jones says the ESIP Federation is heavily involved in cross-domain language used to keep disparate decision makers on the same page. ESIP clusters include semantic harmonization, data quality, disaster lifecycle, envirosensing, and more. You may want to probe to see if there could be some relevant connections. esipfed.org. The winter meeting in January and could be useful, including use cases. Thanks, Dave.
Yes, thank you for that.
And Monique, I don't know if you'll be able to stay on long with us today, but Dave will be presenting on his GeoCollaborate capability between blocks 5 and 6 when we have our break. That's probably going to be a little bit late for you, but yeah, Dave's been a consistent participant in our meetings over the years, and you can look up GeoCollaborate online. You'll find his capability there that he's developed.
Wonderful, wonderful. Look, okay, thank you.
Vince, I did have, there was a couple of comments that I jotted down here. You mentioned speaking the same language, defining terms and so forth so that everyone's using the terms the same way, I think is really important as you're bringing in a new capability and figuring out how to use it. I thought that was a really good comment. And you also mentioned Arif Albanak. I've crossed paths with him just within the past couple months here, and he's been really an interesting person to engage with. So,
absolutely, absolutely, yes, we're very happy to have him.
I guess if there's no other questions, I don't see anything in the chat window here. We can go ahead and move on to the next presentation. And once again, I want to really thank you, Monique, for making yourself available and joining us for this call. So please stay on as long as you can.
Thank you so much. It was a pleasure.
Thank you, Monique.
So now we're going to move on to the next presentation. Let me move forward a slide here. Tim Ball has been with us for, I don't know when you started crossing paths with us, Tim, but I know you've crossed paths with Vince longer than me.
I think it was the second TFRSAC meeting was the first one I came to. And
right.
Of course, I've been afraid of Vince for years. So
well, we all are. So so Tim is here with Chris Schmidt and Dr. Carl Pennypacker. I don't know if either one of them is online with you, Tim, but it's kind of an august group there with Tim being the president at Fireball Companies. Chris Schmidt is a researcher at the University of Wisconsin, and his name comes up frequently in my circles. Oh, there's Chris. Chris comes up frequently because he's involved with Fire Product off of the GOES system as one of his many talents, and trying to improve the GOES Fire Product, which is of keen interest to me. And then Dr. Carl Pennypacker, who's a physicist, and I guess strictly speaking, he's an astrophysicist and is interested in looking at the stars and faint objects. And he came to us and said, why can't we use some of these algorithms that we're developing to find small fires on the Earth's surface? So, Tim, with that, I'll be happy to advance the slides. And
okay.
Anything else you wanted as a preamble before you get started?
No, I don't think so. I think it'll all come out here. So you can go to the next one. One thing I wanted to do before I really get into the AI, and I'm happy to hear Monique talk about the health effects. I've had a couple of occasions this year to be made mindful of the health effects, partly because my own home was in smoke for almost 3 months. And it's actually it's something that I hadn't really given much thought to, but it turns out that the health costs in the United States are heavily weighted against people of low income and of color. And it really is a social justice problem. And the interaction with COVID is a strong influence there. And thankfully, outfits like CARB, the California Air Resources Board, are very focused on this. But it turns out that the cost of those healthcare issues exceed the cost of suppression, the cost of property loss together. I mean, there are just tens of billions of dollars of healthcare costs, and those are things that we have almost never talked about in this group, and I think we should at least be mindful of that. So that was just a little editorial. Hope you'll pay a little bit of attention to that. Next slide, please. So what Fireball and UC Berkeley are doing, and Chris Schmidt is a contributor to our program, is a rapid detection system for initial detection of fires and then ongoing tracking of fires. And the reason that we do this is because it's the most cost-effective way to suppress a fire, to get it early. And what we do is we use a large terrestrial camera network system that uses machine learning to detect fires. And you can see two detections in the same image here on the left. And then we fuse that data with satellite data, primarily GOES, because GOES is a constantly staring asset. And we're doing our work in the area of less than a minute, so we need constant staring assets. So next, and both systems use AI. Next slide, please. So this is the actually just part of the camera. It's actually a screenshot that's late. It was a while ago. There are now more than 900 cameras in California alone, and in the West, it's about 1,200 cameras. We poll these cameras continually, and we do fire detection on them, and we also get the data from Wisconsin from Chris for GOES continually, and we fuse that data. So we have a combination of cloud and edge computing that does this on this large network, and we're now partnering with Verizon Frontline to assure good communication from some of these remote areas and areas that actually have dedicated microwave networks, but they're not necessarily as hardened as the cell network can be under the Frontline system, which is similar to AT&T's FirstNet. So on the bottom there's just a sequence of this sort of a typical fire detection system. The first smoke happened at 3:28. By 3:30, we had notified the appropriate entities, and aircraft and ground assets were launched. And by 3:44, the first air attack was over the fire, and the first air tanker had arrived. And so in those 16 minutes, we basically sped the response by something on the order of 10 minutes by this early detection. And this fire grew to about 250 acres, and basically we were credited with keeping it from running farther up the hill because of that early detection. So you can go to the next slide, please. So here's kind of the numbers. We detect about 65% of the fires that we see within the first minute, and our goal is to get 100% within 10 minutes, and we're up at 99% by 5 minutes. And so the camera network system is over 900 cameras. 60% of those cameras are they're all point tilt zoom cameras. They're basically the same. They're Axis security cameras, different models, but very similar. About 60% of those are sitting and looking at particularly important assets. For example, in Kern County, There's one overlooking almost every town that's in the mountains. And then there are a series, about 40% of the cameras are rotating cameras. They rotate now in 3 minutes. And so our polling rate is twice a minute on the static cameras and 4 times a minute on the rotating cameras. That gives us about 3.6 million images per day that we ingest and scan for fires. So the key thing here is what's the detection reliability. And as far as I think we're the only people that are publishing our data on our error rates, and they're incredibly low. The false positive rate runs on the order of about 1 false positive per million images, and the omissions come in 2 classes. The way we're assessing this is on a distance from the camera. So within the first 10 miles, which is what the camera is supposed to do, we get about 1 loss, 1 missed fire in 4 million images. And a missed fire means it takes us longer. Our criterion is that 10-minute. So if it takes us longer than 10 minutes, we consider that a miss. And we get about 1 in 4 million images will generate a miss. So what that tells you is we may miss a fire about once a day in that 10-mile area, and those fires are tiny. So if you'd wait 15 minutes, we'd get them all. But our criteria is to do it in 10 minutes. For the greater than 10-mile area, we get about 1.5 losses per million images. So a lot more at the 10-mile distance, and that's just to be expected. As I said, they grow faster. If they grow faster, we catch them. But we're really trying to beat 911, and that's people's question. How often do you beat 911? And it's actually probably only about 25% of the time, because people call, which is really good. We're happy to have 911, and we also know that the real limitation on our speed is the rate of camera rotation for those rotating cameras. Now, one thing I should say is that there are tons of people that come forward to talk to the entities that we're working for, and they're providing they want to have a chance to provide their AI. And people come in and say, well, we have 10%, 90% effective. We only have a 10% error rate, or we only have a 2% error rate. If you have 3.6 million images per day and you've got a 10% error rate, you got 360,000 false positives. That just doesn't work. And so this is a hard job. It's a really hard job. And the way we really do this is not with one simple AI algorithm. First of all, we have a very good detection approach. It's highly effective, but we have to set the threshold in that algorithm to a very aggressive point, and that will generate a whole lot of false positives. And so what has to be layered on top of the smoke detection is a system that detects those causes of false positives. Most of those are clouds, and so we have an affirmative AI system that understands what clouds look like and actually tracks clouds in the satellite data, and is going to track clouds on the ground, looking at weather stations. We fuse a whole lot of ancillary data into that system to eliminate those false positives. So that the context, for example, of the fact all the fog in California is coming in on the coast, we have to understand that fog pattern to help us tamp down those false positives. So it's a highly layered. There's actually about 7 layers in the AI system besides just that smoke detection algorithm. Okay, next slide. How am I doing on time, Everett? Guess I'm okay.
Yep, you're doing just fine.
Yeah. So here's the basic way that the system works, and you can see in that left panel, there's one of the cameras, and in the distance behind it, there are two cameras on this particular installation, and the little red box there below the camera is a fire detection, and this is it's actually this camera here on the right that's doing that detection, and its pizza slice is being projected out across the terrain, and then there's another camera that's detected it. So we get a triangulation in exactly the same way that the old lookout towers got it. And in this case, there are 3 GOES pixels here. One of the blue one is a low level one, which is probably diffraction, and the 2 red ones are rated high. And in the middle of that, it happened that VIIRS was going overhead at the same time, and right at the place where the 2 pizza slices cross is a VIIRS detection. So we use all of that data all the time to assess the reliability of the detection, and we convey this. This interface is in the agency's dispatch centers, and they get 2 pieces of information. They get this interface, and they also get an email with each detection. And over on the right panel, I wanted to show you just a little bit about the way we're conveying the information around what the satellite, what GOES does. One of the most important parts, one of the biggest ways we're using GOES is to detect the intensity of the fire. The smoke can tell you about how active the fire is, but the satellite is also very good in terms of giving some indication of FRP. And what we're trying to do is to help the the ECCs, the emergency command centers, to understand that there's data in here that help them prioritize fires. Many times there'll be 3 or 4 fires going on at the same time, and if they have an idea between the camera and the satellite which ones are the most active, they can begin to reprioritize fires. That's one of the biggest problems that agencies have, is not having real-time data that gives them that assessment capability, and we're at least trying to contribute to that. There's a number of things that we're doing. In fact, what we're doing with Chris Schmidt is trying to do some improvements now on the GOES algorithms, and Southern California Edison is supporting that. Okay, want to go to the next one? So this is a really nice example of the way this system is helpful. This is a set of fires from a railroad, from a train coming over the Tehachapi Mountains. It had a stuck brake, and it was throwing hot metal off of the brake shoe of one of the cars in the train, and it started 3 fires. Our detection and the 911 call came in at exactly the same time. But what our detection gave them was this picture. There are 3 fires. And Zach Wells, the deputy chief, has this in his vehicle. He saw this picture and he quadrupled the dispatch to these fires, because 2 things. He knows he's got 3 fires and he knows it's windy. So he knows he's got to drive forward and attack this aggressively. So this provides real-time situational awareness to both engines and officers responding to those fires. Go ahead to the next one. So besides this ground camera network and using GOES, we're in the process of developing, with a grant from the Gordon and Betty Moore Foundation, a geostationary satellite that we actually hope we're going to have a fleet of these around the world, but the Pathfinder one we hope to launch in about 3 years. And this is the sort of shape there on the map is approximately what we think the satellite will look at with a 2.35 degree field of view. Look from the Mexican border up into southern Canada. This is just one of the frames, and normally it would stare at this place. But for example, if there were those fires that they had this year in Canada, we would be able to move the field of view farther up and cover those fires. And in this spring and fall, when Colorado gets more fires, we'd be able to move it to the east. So, but this is not designed to be a scanning system. It's designed to be a completely staring system. It's about, it's actually, I wrote here only 200 times more ability to resolve things than GOES, but it's actually 400 times. The ground sample distance is about 300 meters. You can think of this as a VIIRS satellite that's staring. So it's got essentially the same resolution as VIIRS. And it's about 30 times faster in terms of its reporting rate compared to GOES. It's relatively cost effective. It's about a $220 million problem, and it looks at about 220 million hectares. So with a 5-year life cycle, it's about 2 cents per 1,000 hectares per hour, which is a pretty cost effective way to be able to detect and then respond quickly to fires. Okay, next slide. Here's just some of the statistics. I'm not going to go through them, but they're going to be in the presentation. You can go look at them. What we can find in this with this satellite is about a fire about the size of a city bus, and what that would have a signal and noise ratio of about 87, and have a 3.7 degrees K, which is about twice what the GOES threshold is that Chris uses now. So that same fire would have a 0.6 degrees K delta T with a 2 millisecond read on GOES. So we have a much, and GOES really would not trigger detection of the size of a school bus or a city bus. So it's really the fact that the most important thing is that this satellite can stare longer times and can integrate longer than GOES can. Okay, next slide. In addition to these two systems, I'm in the process of building a wide field multispectral system for airborne science and operations over fires. And this system is going to be used on about 60 prescribed fires in the Southeast this spring. And what we're really interested in doing is measuring the whole fire the whole time and comparing that to the satellite. And this system is basically probably the first airborne system that can get the full spectrum that will not saturate because of the 8-position filter wheel that it has. I can basically guarantee that I can see up to about 3,500 degrees C without saturation. So basically, it's to get the whole the FRP in a solid way and at high resolution. All right, next slide. And I think it's the list of people that, yeah, here are a bunch of the people that have been that are working on this, and it's not just a couple of folks, whole group of folks. That's it, and I'll be happy to answer any questions.
Thanks, Tim. That was great. And it's always interesting to see the things that you're working on. There's a number of questions in the chat here. Vince noted that the slide changes are lagging about a minute. I don't know if you noticed that or whether that's just Vince, but hopefully
yeah,
that
I
wasn't...
didn't notice that. Sorry. Yeah,
okay.
It was fast for me.
Okay, good. So there's a number. Let me start up at the top. I think Prasanna was the first question. Let's see. Let me go.
Yeah, there's something about, are we going to do clutter removal? Absolutely. Yeah, so you have to eliminate the persistent thermal emitters. And to tell you the truth, GOES satellite is the best solar farm finder you can imagine.
That's right. So Prasanna asks, are you detecting only the smoke plumes during fires, or are you detecting other factors as well? And my presumption there was that the system is trained to look for smoke. It's
trained to look for smoke. And the reason is that smoke comes up over hills and flames don't. And so you can see much smaller fires. It doesn't come up even out of the trees. We're trying to see fires before you can see the flames. And they're a much bigger target, right?
Right, yep. Russ Wolf asks, is this system also able to detect smoke at night or during foggy conditions?
Okay, it does work under foggy conditions. It's a battle under foggy conditions. but we do successfully detect smoke under fog because of the shape, or
Right.
and also popping up out of the fog. We can see both. At night, we have not done a lot of training, and we have the data now, but the alert wildfire camera system we don't control. That's controlled by UC San Diego and University of Nevada, Reno. They
Right.
still have the cameras in panchromatic at night, and that's a battle that I have not fought yet. The fact of the matter is that throwing away the spectral information is silly. And so that's really how we're going to do it. You can see that difference in color at night, which is an absolutely perfect piece of information. So we don't have it yet.
Do you, Peter Rincliffe asked if you utilize lightning detects?
We do, yes, we track the lightning detections, and we actually train the cameras, the movable cameras, the ones that are sitting there doing, staring in one place. We begin to rotate those cameras or to point them directly in the areas that we know that and we use two sets. We get the Visala data through the BLM, but we also use that open source lightning detections, and they don't always agree, and that's good because we get extra information from both.
Right. Steve Ambrose from SAIC suggested that the camera system could be used for earthquake detection, homeland security, and general disaster response, situational awareness.
Right. It's actually the alert wildfire system grew out of seismology work, so
right.
they can be, and we have not done that, but it's things like the assessment of damage assessment after an earthquake in like a little town in Kern County, where the camera's staring down in there. These cameras have a tremendous zoom capability, and it's completely useful to do that kind of stuff.
Right. I think I have time for one or two more, and then maybe you can follow up in the chat here. But
yeah.
Karen asks, what is the criteria for detection? Is it temperature difference between the fire and the ambience?
On the satellite, yeah, I think that's probably what that question is. Yes, there is the standard thing on the GOES detection, which Chris is responsible for, is a 2 degrees K above background in the normal situation. The way the algorithm really works is it tries to find a spatial average background, and we want to see a 2 degree K rise above that. If the background's noisier, it requires a larger delta T. One of the things that I didn't mention, I should have. One of the things that we're doing is we're going to follow every pixel all the time in GOES. So we're going to track the entire thing, and we're going to look with AI for patterns of small changes, small fluctuations that are below the 2 degree K criterion, but still are highly likely to be fires. And because we have this integrated system, we can look in other ways.
I'm going to pose one more question because it's from our next speaker before I shift to her. Anshu says, have there been any tests done to understand the downstream impact in terms of fire suppression with this notification system?
No, we're in the process of doing that. I mean, it's a really big question, and it's also hard to assess. And I think one of the most important things to say is what we've seen in CAL FIRE in particular is because they get this information very quickly, it's really changed their ability to think they can make a difference quickly. So basically, early detection is leading to early and aggressive response, which those two things are kind of the keys. They have to go together to really make this useful. And so we're trying to set up a system where we can really track that value that's being added. But it's hard to measure, right? It's a hard to measure thing.
And that's a really important point, because that's something I wrestle with all the time, is what is the value that you're providing to the system by adding a capability?
Right.
And so that's why we've had economists come to these meetings and, look at the capabilities and try to provide us with something but it's still really difficult.
Right. Right.
So
I've tried to get CAL FIRE to let me, when I'm doing mapping, map half the fire and not map the other half. Give me the hard half, I'll be done faster. Right. Because that information is money. It really is.
So thanks, Tim. I think there's a lot of homework for you in the follow-up in the chat session here.
Yeah.
If you want to look down through the chat there, I'd like to turn it over to Anshu Sinha now, and I believe you're working with Josh Mendelson. I don't see him listed on your presentation, but Anshu is a veteran data scientist currently working on data science at Cornea, and is the chief data science officer and general partner at its investment company Hanger. We've also had folks from Hanger engaged with us in the past. Previously, she has founded and led successful data teams at NYC tech firms such as ZocDoc, Vettery, and Hawkfish. She's also an adjunct professor at American University. So, Anshu, I'll be happy to advance your slides, and just let me know. Let's see, do I need to unmute you?
I think I'm unmuted. Can you hear me?
Yeah. Yes,
okay.
We can.
Awesome. Also, yeah, that was a really great talk. So thank you, Tim. And one of the things that we think about too is, and we've been hearing a lot about, is like, okay, you detect the fire, do you let it burn or do you suppress? So really interesting stuff. But on this, hi everyone. So I'm going to start off with the intro that's probably similar to some of the other talks. Oh, and actually, before I do that, I just wanted to mention, yes, Josh, I don't think he's on the call today, but definitely is excited about this and sent his regards. So yes, I will start with a similar intro to some of the other talks, but intensity and the scope of wildfires is increasing, as we know. Average acres burned per year has quadrupled over the last 30 years. And also, as we know, to date, firefighters need more tools to leverage what's out there in terms of technology and what's out there in terms of historical fire data and what's out there in terms of the massive amount of data on weather, ground conditions, and terrain. So how do we put it all together? Our goal at Cornea is to build a set of tools for this area, a machine learning enabled suite of tools to aid in decision making for both emergency operations and planned events. Today, I'm going to be talking about one of our core products called Beacon, which is what we are currently working on developing. And Beacon is a machine learning system for real-time wildfire planning at scale. Next slide, please. Okay, so Beacon basically operationalizes the proven fire science and machine learning that is already out there to predict in real time the scope, scale, and behavior of wildfires. So I'll talk a bit about some of the fire science on the next slide, but it's diving into the metrics that we've already heard about, some in the last day or two. So fire behavior modeling, pods, SDIs, and PCLs. These tools have been used out in the field and they've been promising. They've been used out in the field and for preseason planning, but we know it's sort of been cumbersome to run and track these at scale. They need to be operationalized. And to start, that's where we see a role for Beacon. And I'll talk more about that in the coming slides as well. And lastly, with this platform in place, we believe we'll also be able to provide the needed tooling to iterate quickly to improve the accuracy and quality of some of these metrics. So next slide, please. So first, I'll start with a quick overview of some of the key metrics that we're implementing and rolling out with Beacon. So this is a text-heavy slide, but I feel like it's worth it to do a quick review. The first metric that we look at is Suppression Difficulty Index, the SDI. This was introduced in 2014 by Silva et al. The SDI itself is an unsupervised composite index, so just a number to measure suppression difficulty. It weighs simulated fire behavior against possible suppression activities. So in terms of fire behavior, we use some of the established tools like FlamMap So FlamMap's been around for 30 years and, is well accepted in the field. It takes things like weather, climate, topography, and fuels data as inputs. And so we weigh that fire behavior information against possible suppression activities. So right now, that'll be things like fire accessibility and fire line production rate. So we will, I'm sure we'd love to expand on that, but those are the two that we can do right now. The second big one is potential control lines, or PCLs, and those were introduced by Kit O'Connor et al. In 2017, and that comes out of RMRS in Colorado. So the PCLs are important in creating those pods that we've talked a bit about yesterday. PCLs predict likely fire control lines as determined by these machine learning supervised models. In this case for this, the team has used boosted regression trees. In terms of predictors, it's, there's a lot of primary data for on geo and topography that's included things like elevation, slope, fuels, vegetations, and so forth, plus several composite indexes. So those will be, things like the SDIs themselves, travel cost, fire line construction difficulty. And then we come to the evaluation data. So in terms of evaluation, the team used 238 historical large fires from a 34,000 kilometer square region in the Rockies. And really, these historical fire perimeter lines are what's used to train the model. So both the SDI and PCL have developed decent penetration and trust in the fire community here in the US, and also with a lot of support from RMRS. And so next slide, please. So how are the SDIs and PCLs really used out there? I would say SDIs and PCLs are probably most often used right now in pre-fire season planning, primarily in development of the pod. So how do we effectively position resources to dampen time pressures, to expand options, and then, of course, to protect firefighters? And as we said, real-time generation of SDIs and PCLs is cumbersome, but we can still use those pre-season SDIs and PCLs for real-time operational fire management. Often they're used for onboarding, especially for non-local incident management teams for type 1 and type 2 fires. So for those non-local IMTs, it's pretty valuable. And right now, we also use these SDIs and PCLs for strategy confirmation on things like fire lines and fuel treatments. And lastly, we also think there's a potential future use case for SDIs and PCLs in the planning and development of fuel treatments projects. And I just want to call out the images on the right. They just show examples of a suppression difficulty TIF. That's on the immediate right, and it shows the suppression difficulty with the fire lines overlaid. And then next to that, you see some of the interstitial outputs that we get. And key here is just you can see some overlap on those fire lines, but in general, the actual fire line does stay out of those high suppression difficulty areas. So that's kind of, what we're trying to show. It's working pretty well. So next slide, please. So these algorithms are really promising. But as we said, to date, SDI, PCL, and pod usage has been limited, with real-time use in the field considered just a little unwieldy. So with Beacon, we're building a platform to support these key metrics at scale, and with the goal and hopefully to improve and increase usability. So this is just a list of the challenges that we think we can, that we're addressing and where we feel like we're providing benefits. The first is data storage. So gigabytes of data are needed for each SDI and PCL generation process. So just to use the land fire data that covers the US, it's 9.5 billion pixels with 2,000 attributes for each pixel. On top of that, when there is a real-time fire, we often need to use data that's custom to that individual fire. And that means not just storage, but also ingesting and deploying that custom data. And I think, we probably all have experienced that that's a very arduous and can be a very manual task. So we, not only can we support on the data storage, but also on the ETL that comes with it. In terms of throughput and latency, that's something we've talked about. Again, the time that's required to do calculations on this large scale data can be hours without the right architecture, like many hours and sometimes days. And that limits both the generation and effectiveness. Third on that list is reproducibility. So I would say that there is still a need within the community for better and more standard tools to capture audit trail and versioning info. So I know we've run into this problem quite a bit. There's a lot of moving parts in terms of inputs into these algorithms, whether it's weather data, ERC conditions, different landscape files, and then the algorithms themselves are changing and they're being tweaked, and it's often impossible to go and reproduce results. And we feel that this is so key to being able to iterate and show improvements and show that we are increasing accuracy. So that's something that we want to be able to address. And so that's the last one, algorithm tuning and iteration. Next slide, please. So this is, the architecture that we're building out for Beacon. It's a scalable, flexible architecture that we believe addresses the key challenges in creating SDIs and PCLs. And I'll just kind of walk through this from left to right. But you see all the way on the left there, we have our messaging interface. The messaging architecture is based on AWS Simple Notification Service and SQS Simple Queue Service. That messaging architecture can take in any set of requests. Like right now, it's mostly things like calculate SDI, PCL, train and test the PCL model, export data, and so forth. We like this messaging architecture. It allows us to capture requests as they come in. It provides persistence to those requests and a usable log trail for review. So now going up to the top is our reference database, which we call Oxen. Oxen is storing all the relevant data that we use in these calculations, things like roads and trails data from RMRS, rivers and lakes data from USGS, the land fire data that we've talked about. We also can version these standard resources and be able to track that. We also store our custom landscape files here and transaction data to capture an audit trail for what we've run. Coming around to the side is our file storage, which is S3 and Glacier. So just nothing major to call out there, but just that, using AWS and S3 allows us to have some cheap storage that comes in handy. And then coming down to the bottom, we have our API interface. So we call this triangle, but it's our HTTP API interface for fire behavior data. It actually, for these calculations, we'd like to be able to interface or interface out to some third-party tools for real-time feedback. So it's like interfaces to things like FlamMap, FarSight, interfaces for real-time weather, and so forth. And then right in the middle there is our calculation engine, which we call Macrometer. It's really kind of like the quarterback of this whole system. It sort of processes requests, farms them out to the API interface as needed, gets data as needed, processes those outputs, and then creates the interstitial and final geotiffs for SDIs and PCLs. Macrometer is based in, it's an AWS EC2 system, so we can expand and contract compute clusters as needed. And right now, the average calculation time for a standard fire is about 10 minutes for SDIs and PCLs. Next slide, please. Okay, and this next slide is kind of just reviewing our machine learning pipeline. This is our pipeline to build, train, and deploy models. As we've mentioned, Beacon, there's terabytes of data, and Beacon aggregates this data. As we've talked about, it's roads, trails, and so forth. Calling out also that we'd love to integrate more data as it's valuable. So satellite and sensor data is like stuff we're hoping is what we're hoping to build out on. And obviously we'll build out the capability to integrate in other important and valuable data as we go. Next is we've also developed a flexible architecture customizable, and modular around feature engineering. So key among those features generated are energy behavior, rate of spread, accessibility, penetrability, and so forth. But it's a modular architecture, so we can continue to build on that feature set. And lastly, we are developing a suite of tools to support machine learning model development and deployment, covering standard machine learning models such as regression, random forest, XGBoost, so forth. It also covers hyperparameter tuning. And lastly, it also covers an evaluation data framework. So a strong evaluation data framework is something that we're focused on. We know this is tricky, we know this is tricky. So it's something that we're building out and we'll iterate on as our underlying data improves. And I think this is so key. So we're definitely really focused on this. With this, we hope to provide two things. One is the ability to iterate and improve on metrics with things like champion challenger tests, and then obviously the real-time results at scale that we've been talking about. Next slide, please. And then this one's just a quick one. I just also wanted to call out that we plan to provide UI tooling to help explain the models. We understand that interpretability is key for downstream users. So in terms of the geotiffs, we're including data layers to show things like where there's been fire activity, previous fire history, and STIs and so forth. So we want to be able to help users with decision making. And next slide, please. So, that's the system as it is now, but of course that's just the beginning, and it's we've got a lot on our roadmap as we move forward. So what's next for Beacon? A lot of this has been mentioned throughout this presentation, but just to summarize, I think first, we definitely want to improve the input data that's going into these calculations and metrics, and that will help us to iterate and improve on algorithm accuracy. So again, just call for as people think about them, relevant remote sensing and satellite data. We'd love to connect on that. Second, we want to enhance the algorithm generalizability through expanded evaluation data. As I've mentioned, and I think we've mentioned throughout these talks, it's evaluation is tough. This is real time. There's not as, there's a lot of large fires, but, you have to think about really what's the right way to evaluate and how to plan for going forward. Thirdly, we want to internally develop the capability to run simulation studies via the Beacon platform. So if we can replay large fires accurately and see that the algorithm is working accurately, it just increases our trust in being able to do it prospectively. And then fourth on that list is creating a turnkey ETL pipeline so that we have a centralized data source and real-time ingest. So that's a lot, and it will, obviously, take some time, but that's sort of our high-level roadmap in terms of the technical goals. And beyond that, we just wanted to call out a few more of our strategic goals. We are a new company and just getting out there, so we're obviously focused, on building connections to this fire community. And we want to make sure that we're building value to our key users and to our stakeholders, both public sector and private sector. Next slide, please. So this is the team. I know there are a few of us on the call. I'm pretty sure Margot is here. And it's a small team, but we're growing. And next slide, please. I think that's it. That's all I had on my end, and happy to take questions.
Thanks, Anshu. That was great. Let's see. I'm checking the chat here. We're kind of back on time again, and let's see. Mike Pavlonis from NOAA says this is a general question. The number of new tools is growing at an impressive rate. Can this Internet of Things evolve into a coherent and scalable integrated system? Great question, Mike.
It is a great question. Yeah, if only I had the answer. Yeah, I hope so. But I think there's obviously there's a large investment into wildfire and disaster management, and obviously, it's something that we'll be working across the kind of community to figure out, but I definitely am hopeful. So.
And with that, I think we're going to transition to our next speaker, and we'll keep an eye on the chat here to see if there's any additional follow-ups. I'm loading Angel Farwell Kaus. Dr. Angel Farwell is a postdoctoral research associate working at the San Jose State University as part of the Wildfire Interdisciplinary Research Center. His main interests focus on coupled atmosphere fire modeling, statistical learning, remote sensing, and GIS. He's a co-developer of the coupled atmosphere fire model, WRF-S-Fire, as well as the fire forecasting system, WRFX. He is currently working on projects applying machine learning methods to support fire atmosphere simulations using satellite data conducted by the WIRC modeling group. So welcome, Angel, and I will go ahead and let's see, I guess I need to share this now. So let me bring this up here and put it in the slide.
Thank you so much for the introduction and for inviting me to present. So yeah, so today I'll talk about one of the projects that we are working on in our fire modeling group at Wildfire Interdisciplinary Research Center at San Jose State University. And we aim to estimate fire progression using satellite information, in our case, level 2 satellite data, and using a machine learning method. So next slide, please. So first, let me start by motivating the topic. We have seen a lot of these motivation slices in the previous talks, so I'll try to go fast. Basically, as wildfires become more frequent and more destructive, modeling those fires using fire atmosphere interactions becomes particularly important to assist not only fire, also air quality managers. So to generate accurate fire simulations, we also need reliable input data. And in order to get that, we also need new techniques for processing those observations. So in this presentation, I'll outline one method that we implemented to initialize and assimilate the fire state in a coupled atmosphere fire model. And we use remote sensing and in conjunction with machine learning. So next slide, please. This new method is part of the WRFX system. The core component of which is a fire atmosphere model, which is called WRF-S-Fire. And the system integrates all sorts of data to initialize and assimilate the model. And after the forecast, it pushes all the results into a dedicated web portal and also ArcGIS service for visualizing the results. And in this presentation, I'll focus on this top right red part of the diagram that you see here, which basically shows the structure of the WRFX system. And this red part is basically how we can incorporate fire information to the system using different methods. And in this presentation, I'll talk about one of the ones that we are working on. So if we advance to the next slide. The information that we use is level 2 active fire satellite data, which provides a categorical mask of pixels, and every pixel is classified as missing, no fire, or fire. And also every fire detection pixel has attached some other information which is important for us, like for instance, detection confidence. And we'll see later how this can be used. And this video on the right shows all the overpasses from MODIS, BIRS, and GOES in the California area in August 2020. Here you can visualize it in our dedicated web portal. And we can see in blue the water detection, in green the clear ground detections. Then we can see also some white spots. This is missing data. And then the fire detections are depicted in yellow, orange, or red, depending on the confidence. So the idea is to use this information. So if we advance to the next slide. The main idea of the method is to use this fire and clear ground information and distinguish well between clear ground and missing data. So to explain the idea, here you can see this cartoon in the right. So we have all these squares in a three-dimensional space, which is space and time, and we have them categorized by this L2 active fire satellite data as clear ground or fire. So the idea is to try to find the best separation between burning and not burning regions. And so what we propose to use is classification machine learning method called support vector machine, which it tries to find the best separation between these two categories. And then the decision boundary is going to be our best estimate of the time that the fire arrives at each location. And so in the cartoon, that would be the purple shape, the purple surface. These will provide us a continuous evolution of the fire at any given time. So if we move to the next slide. So here is just to show you how is the implementation, how the implementation was done. The first part of the implementation is actually acquiring all the satellite data intersecting the area and time of interest. And also I want to point out that the method is general enough that we can fit any other information of no fire or fire information in this three-dimensional space. So for instance, if we have infrared fire perimeters, what we can do is define points inside and outside of the perimeters to define more information as clear ground and fire. So then the first part of the method is integrating all this information in a three-dimensional space, as you can see here in this cloud of green and red points. Then we apply some preprocessing of the data. So we scale the data and we perform undersampling of the data of the no fire detections to solve a little bit of the unbalance problem. And then we feed a support vector machine, which is weighted by the detection's confidence. So every pixel, every detection has some confidence attached. So we weight this support vector machine using this confidence. And then this support vector machine provides us with decision function, which is going to be positive if it thinks there is fire there, and negative if there is no fire. But of course, this method was not designed to provide a graph of a function. So at each location, we actually need a time where the fire arrived at that location. So what we need to do is do an inverse interpolation to try to find the minimal root of the decision function. And once we have that, you can see that we get a fire arrival time surface which goes through the detections here in this top right figure, goes in between clear ground and fire detections. And then we can interpolate that into any fire mesh or anything that any mesh that we want to use the data from to get some evolution of the fire. And then we can initialize or simulate these fire atmosphere fire models. So if we go to the next slide. Yeah, this was the previous one. You can go advance 2 slides. Yeah. So
sorry about that.
No worries. So let's see some results from the method. So this year we published an MDPI remote sensing paper that validates this machine learning method. And we used the top 10 largest California fires in 2020 fire season. And then we use this support vector machine method only with satellite information. And then we validate that using infrared fire perimeters. So in the figure on the left, you can see all the areas of interest for all these top 10 largest California fires. So you can see that it's spreading all around California. And then in the middle, in the four figures panel in the middle, you can see the spatial comparisons with infrared fire perimeters. So the top left figure shows the infrared fire perimeters at the different times of the infrared. The top right depicts the satellite fire detections pixels. The bottom left shows the support vector machine method perimeters at the same exact time that the infrared fire perimeters. And the bottom right one depicts the continuous evolution of the support vector machine method. And I want just to point out that the time scale, it's from the start to the end of the August complex fire, which is the case study that I picked to show you out of the 10. And it started from August 15 to October 24th of 2020. So we did exactly the same analysis for all these top 10 fires. And what we can first look into these 4 pictures panel in the middle is that the top 2 figures, they look very, very similar. And this is just proving the capability of using these fire detections to provide a fire evolution. Then both figures on the left show how the perimeters estimated from the SVM are very similar to the ones from infrared fire perimeters. So we are getting, at the time of the infrared fire perimeters, we are getting close to the infrared fire perimeters only using satellite information. And finally, we can also observe that support vector machine also from the 3 kind of disconnected areas where we had fire detections, it only chose to spread some fire in one of the 3. And this was actually the Oak fire, which NIROPS did not map, focus on the August complex fire. So we depicted a little bit of fire evolution there, which was for real, it happened. So other comparison or other ways that we validated the method on is comparing the burn, like using 2 other common metrics, which are burn area and spatial discrepancies. The top right shows a comparison between the continuous burn area from the support vector machine, which is the blue line, solid blue line, and then compared to the discontinuous infrared fire perimeter burn area, which are these colored circles. And it shows a nice agreement. We are still slightly over predicting the burn area, but this is caused by the resolution of the fire detections. But in general, we are fitting the burn area pretty well, and only using satellite information. And then in the plot in the bottom right, we can see the spatial discrepancies computed using the Sorenson's coefficient, which if it's close to 1, it means that there is a good spatial representation, and that's what it's happening using the support vector machine method. So if we go to the next slide, just to summarize and conclude. So we accomplished a fully automated fire initialization using this method in this WRFX system. So we get some fire arrival time maps using this satellite information, and then we initialize and assimilate a couple of fuel, fire, atmosphere, and a smoke model, which is this WRFS fire. And we provide a 30-meter resolution fire forecast with that in near real time. So the videos that are here in the bottom, you can observe like the first video is, yeah, I don't know if it looks like it's not playing, but yeah, it is playing. So these are the fire detections that they are blinking here and there. Then the support vector machine generates this fire progression, which is the video in the middle. And with that, we can initialize the model, which is the last video. And here we can observe the wind speed, the PM2.5, surface PM2.5, and also the fire extent from the method. So if we go to the next slide.
Did I skip one?
I think there was one last
there
one.
We go.
There we go. Yeah. So we use this WRFX system with WRFS fire in this last fire season in the Western United States, and we ran 367 forecasts automatically in CIRA, in CSU and SJSU. And the forecasts were initialized every day of interest at 3Z and 15Z. And this is a complete list of fires that we simulated. And from some validations that we did of the forecast, some early validations, we concluded that it's very important to capture burning pixels in locations of strong winds. And so we really need low latency data for that. And in the videos on the right, you can observe two of our fire forecasts, one of the Dixie fire in our dedicated web portal and the Caldor fire visualized using Vapor. So with that, you can just jump to the last slide. And yeah, thank you all for attending. And I hope you enjoyed the presentation. And yeah, hopefully we have some time for questions.
Thank you very much. Yeah, I think we have time for one or two questions. Let's see. This comes from Neil Leroux. Nice talk. Curious if you're considering using some of the rapid return interval aircraft IR data from 2021, especially for the Dixie fire. For example, 20 to 60 minute updates for validation. Your current results look good for day-to-day changes in the fire area, but curious about intraday variations in fire growth, especially during rapid runs. For example, August 4th on Dixie would be a good time.
Yeah, that's a really nice comment. Thank you so much, Neil Leroux. So that's one of the things that we also want to validate next is how it's doing between day to day, because we think this is where we will gain most of the like we'll use better or the method will be exploited to the maximum. So thank you so much for that. I think that it's a really nice idea, and we'll try to validate further for some of these past season fires. So yeah, thank you so much.
Let's see.
And actually, yeah, related the next question, yeah, if they are available, that would be really nice. So yeah, we'll try to get that and see if we can validate some of the, at least for the Dixie fire.
Okay. Well, Angel, thanks so much for that. I'm fascinated by the work you're doing here, and you've actually brought us to our first break. So thank you for that. Thank you for bringing it home there. And let's see, we're scheduled to come back at 12:55 or 55 after the hour. So that's about, 25 minutes from now. I'll put up a break slide here so that folks know that come in that we are on break until 12:55, and then we'll pick up with our Block 5 presentations, and Cherry and Matthew is our first speaker. So thanks, everybody. We've all earned a short break here. Get up and stretch your legs. Get some food if you're on the East Coast of the U.S., and I guess breakfast maybe if you're on the West Coast. And we'll get back in about 25 minutes here. Okay, we'll be starting up here in just a minute. I gotta load the presentations. Our first speaker is going to be Cherian. Let's see.
Everett, that email I mentioned to you was the second one from Greg Detton about whether he had the ability to control his own slides or not.
Right, right. Yeah,
Okay.
we'll make sure he gets taken care of.
Okay, thanks.
Let's see. I gotta make sure I open the right one here. Okay, it's this one here. That's the right one there. So is Cherian out there?
Yeah, hi. Can you hear me?
I can. Do you want to turn on your video?
I think I have.
I don't see you yet. There you go.
Can you see me now?
I can't.
That's strange.
Let me see. Okay. Can you see the presentation on the screen now?
No, actually.
Oh. So you're logged
yeah,
in.
okay, switch camera. All right. Yeah, I
There you
think
go.
you can see me now, right?
Yep. But you can't see the presentation? It may be on
no, not yet.
It may be on a different tab if you check see if you have more than one Teams link open there.
I can check. I was seeing the slides before on this one.
I don't see the presentation either.
Oh, well, that's operator error on my part, so I apologize for that. Here we go.
No worries.
There we go.
Yeah.
Coming up now.
It's fine. Thanks a lot.
Pay no attention to the man behind the screen. Okay.
That's why we're through it.
I guess we're right on target here, and if so, let me go ahead and introduce you. What I had for you, Cherian, is that you're co-founder and cloud platform lead at Dryad Networks. Is there anything you'd like to add to that?
Yeah, I can. Should I just start off
Sure.
the bat? Yeah, great. Thanks. Hello, everybody, and big thanks to Everett and Vincent again for inviting us back to TFRSAC. It's really exciting to be here. As Everett already mentioned, I'm Cherian Matthew, the cloud platform lead at Dryad Networks, which is a Germany-based startup where we are developing an ultra-early warning system for wildfire detection using a network of ground-based gas sensors, which can detect smoke emitted at the smoldering stage of the fire. Next slide, please. Our primary mission at Dryad is to protect the forest from wildfires by deploying the sensors at scale to monitor vast remote forest areas in real time. In case a sensor detects wildfire smoke, an alert is sent out through our cloud platform, an example of which you can see on the right side of the screen. And this alert contains hyperlocal data, in particular the geocoordinates of the sensor, which can be passed on immediately to relevant authorities to prevent further escalation and control the damage caused by the fire. Although our immediate focus is on preventing the damage caused by wildfires, the network infrastructure we are building can accommodate many other kinds of sensors like fuel moisture sensors, like soil moisture sensors, dendrometers, etc. And this allows us in the long term to collect and monitor data related to the health of the forest, which implies that we can extend the solution to other use cases for the future. Next slide, please. Yeah, thanks. The sensor network that we plan to deploy in the forest consists of the sensor node that you see here on the left, responsible for detecting the fire at an early stage, but also periodically sends out environmental data, which includes temperature, pressure, and humidity. These sensors are connected to a network of gateways, which play the role of routers within the forest to transmit the messages generated by the sensors to our platform running in the cloud. The network is made up of mesh gateways that you see here in the center image on the left with the solar panel, which act as internal routers not connected to the internet, which pass on the sensor data to border gateways seen here in the center image on the right, which are placed at the periphery of the forest and are connected to the internet. These border gateways send the data to our cloud platform, which is responsible for managing the devices as well as for monitoring and sending out the alerts. The actual time taken by the sensors to detect the wildfire smoke is not easy to estimate, as it's very much dependent, of course, on the wind direction, on the wind speed, and the volume of smoke. But we are aiming for, on average, a sensor being able to detect smoke at a distance of about 50 to 80 meters within 30 minutes to an hour. It's also important to stress here that we look at our solution to be very much part of a broader ecosystem of solutions aimed at solving the fire detection problem, as we are seeing here in the TFRSAC meeting. And we are locating ourselves on the early warning part of the spectrum with the added advantage of hyperlocal environmental data. The sensor gateway network that we are building is built on a mature and reliable technology specification called LoRa, which stands for long range, capable of sending smaller message payloads, but over very large distances, which is ideal for a use case like ours, where we plan to deploy sensor nodes in the remote parts of forests where we do not expect to have any kind of mobile coverage. The entire solution is custom built within Dryad and is branded as Dryad SilverNet. This includes the PCB design of the sensor nodes and gateways, the embedded software running on them, and the cloud platform, which includes a web plus mobile application and a multi-purpose backend. Next slide, please. Our smoke detection pipeline starts with the sensor node with a built-in gas sensor, which is the cutting-edge BME 688 from Bosch. This is a metal oxide sensor which can detect volatile organic compounds, which are essentially substances of organic origin found in the air in gaseous and vaporous form. And of course, wildfire smoke is one of those volatile organic compounds. The output of the sensor is a resistance value in ohms, which changes according to changes in the surrounding environment. In our case, this is, of course, the wildfire smoke hitting the sensor. This value is in turn used to generate a secondary metric computed by a library provided by Bosch, which takes into account historical trends and gives us an indication of the air quality. This IAQ value is then used as a first phase trigger, where we simply use a threshold to determine any significant change in the environment. This phase does not identify wildfire smoke, but just provides an indication that there is some disturbance in the surroundings, which could potentially be wildfire smoke. Once the first phase is triggered, resulting in a yellow alert, this leads to the activation of the second phase, where the machine learning process kicks in. Here, instead of one reading, we take a series of readings, so a series of resistance values, 10 in total, which is validated against our trained machine learning model. And if the model qualifies this as smoke, we send out a red alert. Next slide, please. For the machine learning pipeline, we have been and continue to conduct experiments to generate training data for the wildfire smoke detection model. These experiments are done using the same sensor nodes that we deploy in the forest, but with a configuration optimized for training. The experiment protocol usually includes taking a number of clean air samples at the start, burning forest fuel material on a hot plate, and then recording smoke samples. We have been doing these experiments in our smoke chamber, which is a closed control environment, as well as a large hall, which allows us to test distance and volume of smoke. Recently, we also have started experiments in the forest for actual real-world data. And the samples then from the experiments are then sent to our cloud platform, which stores the data in an indexed data store. We then download the data and feed it to the Bosch BME AI Studio, which is a tool built specifically for the BME 68X series of sensors to generate the model, which we then deploy to the sensor. Next slide, please. The BME AI Studio builds a neural network-based classification model to classify clean air versus smoke, which also gives us the possibility to train and verify the neural net. And of course, it provides the standard metrics of the classification model like accuracy, F1 score, etc. Next slide, please. So as with all machine learning solutions, we have of course faced a number of challenges in building a reliable model to detect wildfire smoke. This includes to begin with the experiment design complexity, where we need to generate wildfire smoke in a controlled environment and ensure that we are able to simulate the real world scenario as much as possible. We've also struggled a bit with recording valid clean air samples, especially in the indoor venues. That's the smoke chamber and the hall experiments, where we found it difficult to eliminate the smoke completely from the environment in those venues, and which means that most of the clean air samples that we've taken there are actually a bit smoky, so to say. This has become now easier with the experiments in the forest. The difficulties in conducting the experiments also means that we could not record a large number of samples yet. And the clean air issue also leads to the problem of data imbalance because we have more smoke, valid smoke samples rather than clean air compared to the clean air samples. But we are trying to mitigate these problems by moving to the forest, trying to have much more controlled data. And of course, now the more we understand the problems that we've seen, we can solve them much easily, and also go for getting more data samples from the experiments. Next slide, please. So these are the results of our latest models. Of course, I wouldn't read too much into it at the moment, except for the fact that we believe we are headed in the right direction. The results look positive. We are aiming to get a model which is very low on false negatives, so not detecting smoke when there is actually smoke, which would be very bad for a solution like this, of course, and tolerating a slight amount of false positives where we are detecting smoke when there is none. So again, yes, work in progress, but we think we're headed in the right direction and hopefully having much better results in the weeks and months to come. Next slide, please. Yeah, so that's the end. Just before I finish, a quick status on where we are in our journey at the moment. So we have already signed a number of proof of concept pilots planned for deployment at the beginning of next year. These will be generally small deployments with one border gateway, one mesh gateway, and about 16 sensor nodes. And these includes installations in Turkey, in Sierra Leone, and the United States. We had mentioned in the earlier TFRSAC meeting that we had successfully closed a seed funding round a bit more than a year ago. We are also now currently in negotiations for Series A funding, which we hope to close early next year. So with that, I'll end. And thanks again for the opportunity to present today, and I'm happy to take any questions.
Well, thanks you, Cherian. That was a really nice presentation, nice and concise. And I do see, let's see, there's a question from Vince. Vince, do you want to pose your suggestion there?
Yeah, sure. It was just a comment where I could see this expansion of the system to other applications, such as along pipeline right-of-ways to measure leakages. But that, of course, would require change in sensor band characteristics, so you're measuring specific species. And also, as you said, I just noted in hard-to-reach areas, I guess you work in Sierra Leone and other places like that. So, yeah, very applicable. Thank you.
Thanks a lot for that, Vince. Yeah.
Let's see, there's something from Paul. I just scrolled off the screen here. With LoRaWAN being a star network, you are limited in range. Have you plans to change the architecture of the network, the mesh networking, to extend the coverage of your system? And
yes,
he says,
in
fact,
sorry.
He says, P.S. I'm a PhD student working, wanting to work on sensor network using LoRa.
Okay, that's really exciting. Actually, it's a really exciting technology, and the specification itself includes only devices, so like our sensor nodes and the gateways, the border gateways that I've mentioned. The mesh gateway is something that we have introduced into this into the network, which will allow us to, in fact, increase the range of the message sending. And this is a patent which is pending. We are developing this at the moment. And this will allow us to deploy sensors in very remote areas, use the mesh network as mentioned, internal routers to hop the messages across many mesh gateways, eventually reaching a border gateway. So depending on the resolution that is required, we would be able to scale, we would easily able to scale even in large forest areas.
Let's see. Haroon Stephen from UNLV says, what is the sensor sensitivity to the smoke and soot density?
That's a very interesting question, which we're actually trying to solve right now. This is, like I mentioned, a cutting edge sensor, which uses machine learning. No other sensors in the market usually have this machine learning possibility. But it's something new that the sensor this use case is kind of new for this sensor, and we are also ourselves trying to understand the sensitivity to smoke, to wildfire smoke in particular. The results currently seem good, but we are now looking at distance and volume of smoke. And as soon as we have more results, I would be happy to present this later.
We have time for one more here. This comes from Neil Leroux. Any thoughts about distinguishing between prescriptive burns and wildfire so alerts aren't sent for non-emergency situations?
That's a very tricky question. This differentiation of the smoke is something that we have been discussing recently. We are in fact getting forest material from different parts of the world where we plan to deploy. So we would train the models for those. If it is possible to have a very specific signature of the smoke for the prescribed burning, I would think this would be possible, but otherwise it would be, I would imagine, difficult to distinguish this.
Yeah, I agree. I think that would be very difficult, and that would require that folks that are receiving the alerts are aware of the fact that there's a prescriptive burn going on,
exactly.
And knowing where that burn is taking place, knowing what the weather conditions are, and so forth. So
exactly, yeah.
Let's see. How do you distinguish smoke from methane?
That's exactly what this. I mean, the normal gas sensors stop at the first phase, where you would imagine it would be difficult to distinguish, and you only get an IAQ value, which tells you that there's something wrong. But the machine learning part, which allows us to have this heating profile, to heat the sensor in 10 steps with different temperatures. You can have different heating profiles, which will allow you to use these 10 values for different use cases. And it surprisingly distinguishes between many different kinds of volatile organic compounds. And smoke is one of them. Wildfire smoke is one of them. So there would be a distinction based on what it reads as training data.
Well, thank you, Cherry. And that was a great presentation. And we're going to go ahead and move on to the next presentation by Andre Coleman.
Thanks.
Let's see, Andre, where are you, Andre? There you are. Has served as a senior research scientist with the Earth Systems Predictability and Resiliency Group at the Pacific Northwest National Laboratories since 2000. He brings 26 years of experience in the fields of remote sensing, spatial modeling, hazard informatics, hydrology, high-performance computing, and statistical machine learning. A majority of his current research is focused on heterogeneous data fusion for rapid disaster assessments. So go ahead, Andre. You have 15 minutes, and I'll go ahead and advance your slides.
Perfect. Thank you. Yeah, and I guess maybe just to start out, thank you to everybody who has participated in this meeting. It's every presentation, all the comments have just been incredibly valuable to me, certainly. So I wanted to take the opportunity here today and thank you for allowing time to present on this. But a tool set referred to as the rapid analytics for disaster response, what we collectively call radar, and so some of the work here is specific to the wildfire module within radar. Next slide, please. So just to give a little bit of a background on radar itself, that this work builds on 7 or 8 years worth of research. This was originally spun out of the Department of Homeland Security's Science and Technology Division as a 2 or 3 year project, really with the objective to develop an all hazards system that relied on remote sensing observations, to be able to produce damage assessments within 24 hours of the start of an event. And then to be able to carry those assessments on as frequent as possible after that. So a lot of the original intent of radar was really focused on hurricanes and cyclones, flood events, wind events, tornadoes, in earthquakes. Wildfire has always been a component in here, but really probably in the last year and a half, there was a lot of emphasis put towards improving the capability of wildfire monitoring. I will mention that the Department of Energy's Cybersecurity, Energy Security and Emergency Response Office, otherwise known as DOE CSER, currently supports this work and the continued research and development on it. And you may wonder why DOE for some of this work, and it's really focused on hazard analytics in response to critical energy infrastructure, as well as other community lifelines there. So understanding how those hazards may be impacted or have already been impacted. Certainly with the increase with the electric grid and impacts there with wildfire, this has become more and more important in the space. So since 2016, radar has been used on over 50 major disaster events, not including wildfires. And then with this this season, that adds many hundreds more events to the system. Next slide, please. So with the wildfire work, this was really prompted, I would say, more by a White House effort that was started in early 2020. I think there's a few folks in this meeting today that were also a part of this executive forum or task force. But this was really an effort to understand how AI-based technologies could be used to help in disaster response, situational awareness, help improve that kind of information for first responders. So from this work, we ended up working then with the DoD's Joint Artificial Intelligence Center and DOE's Artificial Intelligence Technology Office. And through this effort, then what we ended up building out specifically for wildfire is a completely automated end-to-end system. It's cloud-based, scalable. It's an open data solution that really focuses on retrieving satellite imagery from a number of high-resolution EO satellites. So from that imagery, then we run AI analytics to generate standard mapping products that can be used out in the field. So one of our objectives outside of using a set of high-resolution sensors out there was really to contribute and advance that situational awareness and the cadence in which that situational awareness is being delivered to get at specifically active fire fronts, spot fires, scattered heat, unburned areas, and a few other things, including a preliminary burn intensity product. And the idea was to really understand, well, how can we complement the current aircraft imaging that's going on, and help to not only increase that cadence, get multiple collects during a day, but also be able to fill gaps where aircraft aren't able to get. So with all this in this complete end-to-end system, this system also includes the dissemination of the data through website, through an API. There's a mobile app associated with that as well. So the graphic on the bottom just really illustrates some of the notion here of using satellite, high-resolution satellite sensors to collect that imagery, getting into sensors that are really focused on shortwave infrared and beyond, and taking that imagery then and producing an analytic product that is small in data size, so it can be transmitted easily under low bandwidth requirements. Next slide. So when we started this this effort, we had the typical satellites that we were using for other kinds of hazard events, but we decided to take maybe a step back on this and say, well, what else is out there perhaps that we might be able to utilize, and really with this idea that we want to use a lot of different sensors really to help fill that cadence issue. As I think folks probably well know, a number of these satellites maybe only come around every 5 days, and so being able to combine multiple satellites to the point that we can get multiple collects in a day was definitely a goal. So things like Sentinel-2 were kind of a mainstay. We also use Sentinel-1 SAR to implement an approach there, which really has a great benefit. Any SAR sat that we can get through the cloud cover, operate in day and night conditions. There's also a couple of experimental sensors out there that are on the International Space Station, such as JEDI, which we were really using more for getting at vegetation conditions, so maybe a little bit different part of the work, and trying to develop data to help parameterize and provide just-in-time data for fire propagation modeling. But we also have EcoStress. EcoStress wasn't designed for fire. It had all the right properties about it though, and really ends up being a really great asset with about three or so collects a day over the western U.S. So of course we also have Landsat 7, Landsat 8, Landsat 7. We did, although that's a mission that's going to be retiring, but the one of the issues we have in Landsat 7 is scanline dropouts, and so we did develop some code around that to help fill those gaps. CBERS, also for those who know that sensor, it doesn't collect in the U.S., but it collects in other areas of the world. And I probably should have mentioned earlier that with the idea with the design of this capability is really to collect and provide these analytics not only in the U.S. but truly anywhere around the world. I'll also note that the system that we developed, while our initial focus was really on more open data type sensors, nothing really precludes from ingesting commercial imagery or airborne imagery or UAS type imagery. Next slide, please. So just to give a quick view here, satellite timing and coverage. One of the great things with satellite is sort of the extents, spatial extents that we can collect in one shot. So on the left here is an example, Sentinel-2, collecting 7,100 square miles in a single scene. So some of the advantage there, right, is we can pick up on multiple fires and provide those analytics all at once. Sentinel-1 there on the right, can collect a huge ground area in a minute and a half. There are still latency issues with getting that data transmitted and made available for analytics, but in general we're seeing probably about a 4 to 5 hour latency between image collect and image availability. And our system is set up such that including the image retrieval, the analytics, that's about a 5-minute process per scene that comes in, and then another 2 to 3 minutes to disseminate that data out to services and log that into the data APIs. Next slide. Just another example, a different sensor that we've integrated and taken advantage of, and that's AWIFS. So that's at a 56-meter ground sample distance. Why I wanted to show this image is just the significance of the amount of area that it collects in a single scene. So here, July 15th of this year, we had one single scene that captured 153 active fires, which at the time was 24% of all active fires. So in one single scene, there's a lot that can be done really with 10 minutes of processing to get that information out across this area. Next slide. One of the other tools that we have integrated into the system is a satellite forecasting tool. So it's really important to be able to understand and know when to expect collections. And if using the system in combination with airborne collects, maybe understanding that, well, perhaps you've got a gap in time for airborne collections, or a gap in time with satellite collections, and maybe you want to get airborne in there to supplement. So just another type of planning tool here. Next slide. So just a quick example. This is on the bootleg fire. Started on July 6th. The NIFC mixed method heat perimeter came out on the 7th at 2030, and our radar system logged that fire and was able to grab Sentinel-2 imagery 15 hours later. And that's the pink delineation there. So you can see in that short amount of time how quickly that fire has moved out already. Next slide. So I really wanted to just emphasize, this idea of bringing multiple sensors together and being able to get data that's being provided, multiple times a day. And really quickly here, we've got a number of different collect methods, including the initial mixed method heat perimeter. Once that boundary was delineated, we had a Sentinel-2 collect that came 6 hours later. And then 9.5 hours after that Sentinel-2 collect, we had VIIRS that collected. From there, we had the NIROPS flight 43 minutes after that. And then 3.5 hours beyond the NIROPS flight, we had an eco-stress collect. So, it's really a great tool to be able to get at the fire dynamics here and do better than the once a day collect or twice a day collections. Next slide. So the mapping products that come out of the system are pretty well represented in the slide. We're using the standard mapping classifications of intense heat perimeter, scattered heat, and isolated heat. The final products come out in a vector data set in a number of formats, KMLs and OGC web services. There's a data API that you can connect to. There's an application you can get at the data. We also tested retrieving data through the ATAC Civ application. And there's also metadata API associated with that, so you know exactly when the image was collected and what time this data is representing. Next slide. So some of the other variants on the work beyond just the fire mapping is we developed out a fire retardant model. So using the exact same imagery that we're pulling for doing the fire mapping, but also extracting specifically retardant lines as they come out. We've had really, honestly, pretty good success with delineating these, and I've had some interesting finds in finding fire retardant lines that were dropped that weren't recorded, and so forth. So more work to be done there, and adding more landscapes into there, and just better training up that model. Next slide. Additionally, we did some work also with the BLM in early fire detection with these same sets of high-res sensors, and yeah, great tool I think for more wilderness areas and places where we don't have ground cameras and so forth. And last slide, I just want to next slide. Just want to highlight the use of synthetic aperture radar and really this tool to be able to get at burn area conditions, be able to get full heat parameters from SAR, again, day-night conditions, cloudy conditions. And so this becomes an important sensor in the mix here. So I'll leave it at that, and thank you for the time.
Yeah, thanks, Andre. That was great. And are you going to be able to stay around for our open lead discussion?
Yes, I'll be around.
Okay, thanks. I'm getting an echo right now. So if someone has an open mic, there we go. Let's see. It looks like you have some backup slides. I'm going to just, okay. And so now I believe for Vince, can you introduce Emilio while I bring up his presentation here?
Yeah, I got it, Everett. So next presentation is from Emilio Pineda and Enes Seton. And Emilio is the CEO of Volant Aerial, which is a global innovation company at the intersection of unmanned vehicle systems, computer vision, and the Internet of Things, and collaborating with Dr. Ahmet Enes Seton at the University of Illinois, Chicago, and they will be speaking on AI for early detection and georeferencing of fires, and to give us an update on that activity that they're currently engaged in. So with that, looks like the presentation is up, and I'll hand it over to Emilio and Dr. Seton.
Thank you, Vince. It's a pleasure to be here. We're very excited. We also presented on the last session of TFRSAC, so it's really good to be a part of the community. And the idea of our presentation this time is to show you the advances that we have made on an AI for early forest fire detection that can be applied to any camera, whether it's cameras in towers, drones, planes, or satellite. So let's move on to the next slide, please. We are a group of engineers with UAV and remote sensing experience, and we partnered with the University of Illinois at Chicago, specifically with Professor Ahmet Enes Seton, who will also be presenting with me today. And we have been awarded grants by the National Science Foundation, and we have also coursed the I-Core program, in which we essentially mapped the ecosystem of fires and got the top priorities for early detections, which we are trying to solve. Next slide, please. So we are highly focused on three main objectives for our AI software, which are detection, georeferencing of the fire, and sending alerts. Okay, this means accurate detections, low false alarms. This means an accurate georeferencing of the fire that started even from a single camera, and being compatible with existing systems to send the alerts. So we're not reinventing the wheel or creating another cumbersome login and another platform that first responders have to log into. Next slide, please. These are some of our general specs of what the system can achieve. So 24/7 operation, meaning we do detection day and night. From a single camera with good conditions, we can cover up to 700 square miles. We have a tile pattern AI, so we can run essentially the AI many times in a single frame. We are compatible with existing systems. We can have the ability to record footage prior to the fire starting, so that it can be used for evidence or further studies, or even used as a data set for retraining the models. Next slide, please. So talking about training the models with AI, it's very important to have a vast data set, right? We have put a lot of effort into acquiring as many assets as there possibly are in the world of fire starting from many different perspectives. But the truth is, there's just not enough. We need in the order of millions of assets to really create something very, very precise, which is what we want. So we have created novel methodologies to create synthetic data sets that we use to retrain our network and then test against the real videos. And this has proven to be very, very successful in increasing our accuracy and lowering our false alarms. And we have been able to filter clouds, sunset, sunrise, fog, and many variables that just happen with these cameras. Let's continue, please. And speaking about georeferencing, we created our own model that integrates the digital terrain model, or essentially the mapping of the terrain, whether it's already available or we create it ourselves by the use of drones. And we integrate this into our own software that leverages the camera's position and azimuth to triangulate the exact location of the fire. And we are trying to expand this so that in a live view, the user can actually circle around the fire and create a boundary. That would be very, very useful to know exactly where the fire is located and what the edges are in real time. Let's continue. All right, I'll let Ines take it from here.
Okay, I just unmuted. Okay, thank you. So we have two wildfire detection software based on deep neural networks. And these are actually interpretable deep neural networks. The first one is based on just a single image based detection, and this is for stationary and moving platforms. And the second one is a spatial-temporal video based on spatial-temporal video processing, and it uses multiple image frames. And we have a novel algorithm capturing the meandering smoke behavior. And our software capable of detecting the wildfire at day and night. Next slide, please. Okay, so Emilio also talked about this. We divide the image into small tiles, and these tiles are overlapping tiles. We can run this system on embedded computers. We have tested this, and we can process 1K by 1K image in about a second right now. Next slide, please. So this is a highly technical and busy slide, but our methods are interpretable. We use the image processing or signal processing background that we have. We've been working on wildfire detection since 2005. And collected data from Turkey and Mediterranean. Our work was funded by European Union. And so we take the currently available MobileNet V2 or V3 network. These are developed by Google, but we don't use them as they are. We have our own schemes embedded into the MobileNet V2 or MobileNet V3. And we have also tested our algorithms in other data sets. So this is, and we improve the performance of MobileNet V2 and V3 in other publicly available data sets. You see, MobileNet V2 and V3 are developed for object recognition, like face recognition, vehicle recognition, etc. They are not suitable for smoke detection, so we have to retrain them. This is called, in transfer learning in machine learning or AI literature. But in addition to that, we modify the network and we introduce our own layers into the network. Next slide, please. Okay, so these are some of the detections that we tried on HP-RAN, but we have also our own data set that we obtained from Turkey in collaboration with the General Directorate of Forestry in Turkey. Next slide, please. So here is another early detection result. Next slide, please. These are done, by the way, using the single image frame method. Next slide, please. Okay, this is a night fire detection result. So our cameras can work on night as well. Next slide, please.
So
okay.
we chose the HP-RAN camera network to show you these tests today because it's very well known in the industry that these cameras are around, and the images are easily accessible, publicly accessible. So we run some tests. We get about a frame per minute from these cameras, and here is the results that we achieved in detection time in minutes starting when the smoke is barely noticeable in the image. So as you can see, everything is under 15 minutes, which would be greatly improved if we would install the AI on an embedded computer in the actual camera, and we would be running our system every second rather than every minute, so that we can go through all the filters to eliminate false alerts. Okay, let's continue to the next slide, please. So here we tested the false alarm rate in very challenging conditions. And the biggest challenge is that smoke is an abstract variable. It takes any shape. So it's easily confused by an AI with fog or clouds, right? So we're working really hard on reducing the false alarm rate. Right now we have less than one false alarm per day, and we expect to reduce it even further by using the following method. And I'll let Ines present. Please, next slide.
Okay, actually this the image on the left is a false alarm here due to fog. The image on the right is, there is a fire here. It's barely visible on the right, but our system detected it. And when we use temporal information, we can get rid of the fog. And we have a novel way of doing it. We have two-stage processing here. You know, video is actually a sequence of frames. So we have a cube of data. You see, image is just a plane. And when we have video, we have a cube of data. So we take slices, vertical or horizontal slices on the data. Next slide, please. So for example, here, the one on the left is a false alarm, and the one on the right is a temporal slice obtained from the video and from the same small fire. As you can see, we have this meandering smoke behavior captured by the temporal slice information. So we don't process the entire video. If we process the entire video, it'll take forever. But we just have a cut, horizontal cut over time. So we create this image here. The ones on the right are the images detected from horizontal cuts, horizontal temporal cuts. And then we feed these images into the AI algorithm, deep learning algorithm, together with the actual images that we observe. And that's how we can achieve high recognition rates, and we can eliminate false alarms. Now, this meandering behavior, that's why we call our system an interpretable AI, because we not only have algorithmic level interpretability, but also we have image level interpretability. We clearly identify the temporal behavior. You know, take a look at these red arrows. Okay, the meandering smoke behavior is definitely different from fog, and AI algorithms can take advantage of that and recognize smoke and distinguish it from fog and other stuff. Next slide, please.
This is a video, so I think you have to click on it to play, please. So this is taken from HP WREN camera. This is just to show you our system in action and how it operates at night and day. And you will see clouds and fog throughout the course of the video, and it doesn't trigger any false alerts. And then we will have an actual positive fire detection. Keep in mind that sunrise and sunset are really difficult because they create these objects in the image that can be read as fire by AI models. So as you can see, we've solved that. We've also solved low clouds and fog. And any moment now, we should be having real detection. There is the detection, and it was, if you notice, it was actually detected way before the human eye could notice it in the image. Okay, we can move to the next slide, please. So to wrap it up, thank you everybody for listening. We are open to collaborations. I put a message in the chat with one of our emails, so you can reach out if you have any questions or ideas. And the main objectives for our software are to accurately detect, georeference, send true alerts, and be compatible with every existing system today. Thank you very much.
Well, thank you, gentlemen. I'm going to go ahead. Let's see. Okay. I don't see any questions. I do see a comment there that impressive by Deepak. Alex Koltanoff says, I wonder how effective the method is when there is significant background motion, not a still background.
So that's why we have two models running simultaneously. One is for moving platforms where there will be a lot of background activity. So that one analyzes a single frame at a time really quickly. And then we have another more suitable for stationary cameras where the background doesn't change, but the smoke does a lot more, which is the spatiotemporal that we just showed.
Let's see.
We are working on moving platform-based spatiotemporal analysis right now. It's our current research.
Staff Sergeant Gomez asks how the alerts are disseminated.
The alerts are disseminated by any of the existing systems. So it could be an email alert. It could be tapping into systems like ATAC, for example, Android Tactical Awareness Kit, or even the ArcGIS license that the fire responders use, which is purchased by the government, essentially. So yeah, go ahead.
I was going to say just one more question here. Deepak says, I wonder, I might have missed it, but what kind of day and night false, oops, it just scrolled off there. What kind of day and night false alarms and what rate do you experience daytime versus night, I guess, in terms of false alarms?
That's a very good question. So both of them combined are less than one a day. but there is bigger challenges at night because we are detecting the glow of the fire rather than smoke. So there are other issues to solve. Right now, we're focused more on day, but the system is still working very well on night.
All right, thank you, gentlemen. We're going to need to move on to the next presentation, which is Greg Denton. And Greg, if you're there, you should see an up arrow at the top of the screen where you can, you wanted to run your presentation. So if you see the up arrow just in the upper right-hand corner near the red block, there's a little square with an up arrow. You see that?
Yeah, I do. Thanks, Everett. Just getting it going now.
And I'll go ahead and introduce you with your bio. Greg is a business leader responsible for the fire intelligence segment at Overwatch Imaging. He works to bridge the divide between engineers, academics, and end users to deploy innovative solutions in the field of remote sensing. And I guess I'll leave it there for now, but Greg, welcome. And I'm very intrigued by your broad reach there and your experience and your work there. So go ahead.
Yeah, thanks a lot for having us today, Everett and Vince, for organizing this group of people to come together. As everyone has seen over the last couple of days, there's so much development and work happening right now in this field that it's more important now than ever to kind of break down barriers across silos and figure out exactly what's happening. There's so much opportunity for collaboration. So I'll provide a deep dive into some of the work that we're doing today, focusing on actual system performance rather than kind of future focused kind of blue sky initiatives. And I would encourage anyone kind of listening today to reach out to me. My email address is gregory@overwatchimaging.com, and let's start the conversation. So in terms of performance this year, Overwatch was active on about 2,300 missions across the United States through our partners. So Overwatch Imaging provides a aerial sensor platform, which is a combination of hardware and software, which provides a broad capability of remote sensing and artificial intelligence for agencies. So in terms of scan rates, these are kind of aircraft-based systems. You can scan millions of acres per hour at meter level resolution for thermal imagery. So to kind of put that in context against satellite image sources, those are several orders of magnitude higher than what's available from satellite sources. And the devil is in the details. When you have additional detail, you have additional problems to work through. And so I'll show some imagery and kick off a discussion about artificial intelligence from there. I guess I should add that these are the most widely used sensors in the US market today, providing around 85% of aerial fire mapping missions in support of the NIROPS program. These data are sent air to ground with around a 2-second latency or kind of provided hours to minutes after the aircraft arrives on site. So I think I wanted to start off kind of at a broad level of what is artificial intelligence. The term gets kicked around quite a bit, so I wanted to be specific about the work that we're doing here. In terms of AI here, let's just get my slide. So yeah, the development of computer systems able to perform tasks that require human intelligence, such as visual perception, speech recognition, decision-making, translation between languages. I'm going to focus today on that visual perception component. The term we use is computer vision. So we understand imagery by breaking it down into different constituent parts and then take action based on that image recognition. And I think we also need to talk about automation in this effort. Because the fire community, has to operate at scale. We often have events kicking off across a very large geographic region, and the scale is difficult to manage if you don't have an automated intelligence system. So in terms of the talk today, I'm going to focus on the idea of a broad artificial intelligence as opposed to a narrow artificial intelligence. And the differentiation is the ability for a system to perform one very specific task very, very well would be a definition of narrow intelligence. And that's something that you've seen kind of across the board where you have images broken down into constituent parts. You kind of create a grid, and you're able to detect a very small smoke signal in that array. So I think that paradigm is very well understood. We've seen a couple examples of that operating very successfully today. You place cameras or geostationary satellites in view of a scene, and when the smoke appears, you get an alert. That's a very powerful and kind of well understood system. That is just kind of one of a suite of models that can operate on board Overwatch Imaging's products for new fire detection from an aerial source. Aerial sources, of course, have the ability to detect kind of 6-inch targets at altitudes of 10,000 feet, as opposed to kind of school bus or house-sized targets. So the ability to detect fires at a much smaller scale. Here's an example of that wide area object detection working over a thermal raster. So you kind of fly over this scene, scan the area. Small boxes are placed very rapidly around targets, and those targets can be communicated to people in the field. And that work is being done today in California. In terms of broadening intelligence from that narrow view of artificial intelligence and kind of broadening the scope of capability, Overwatch is focusing on a suite of applications for the firefighting community. So those range from post-lightning patrol. You have a lightning storm come through, and you go scan the area afterwards to find new smoke and new heat sources as soon as possible. Of course, fire mapping is a large initiative. But also burn severity estimates post-fire, new fire detections, damage inspections, and fire line perimeter creations are all part of a broad suite of applications that run on the same hardware. So software modules and machine learning modules can be developed to run on top of hardware. And so the system works much the same way as you would give in instructions to somebody in the air today. So, hey, we need you to go out and do a reconnaissance mission, or we need you to do a fire perimeter creation mission. And then the system is able to take action based on those instructions.
Hey, just a quick interruption. We're only seeing the bottom half of your slides here.
Oh, shoot.
I don't know if you have two screens open or what the case may be, but perhaps if you stop sharing and then reshare it again, it'll come up properly.
Yeah, we don't want that. Let me see.
Yeah, we were seeing some black and white figure there with a half black sphere and half white sphere. And
shoot, looks like there's a bit of a different experience for some of the guests, but let's try this way. How about now?
That looks good. Yep.
Great. So after the introduction there, kind of placing Overwatch and our work in artificial intelligence, I'd like to dive into a very practical application. And I think arrive at a point that I'd like to communicate to this entire group today is that the definitions are very important. So kind of academics and researchers can create definitions of data products, but it's so important for the user community to be involved in that process as to kind of the nuance associated with the result. So I'll take this application of fire perimeter creation is a very simple thing, but it's not easy to do. So that could be interpreted as draw a circle around a fire or containment line around a fire, or where the fire has been and hasn't been, or where the land is burnt and not burnt. I think with that problem, we kind of assume that you can turn this continuous variable into a discrete or binary one. It is or is not burnt. And we also assume that fire moves kind of in a linear pattern, A to C through B, that fire is linear. And of course, for anyone who has worked in the industry, fire is not linear. It jumps and it moves, and it is also sometimes not easy to differentiate between a burnt area and an unburnt area. So here's just an example of that. There's a NIROPS fire perimeter from mixed sources that is outlined and contrasted against an NDVI image backdrop, where you can see a lot of nuance to where the fire has been. So simply creating a fire perimeter is not always kind of a straightforward application. You can see areas where the fuel consumption is complete, represented by the mineral soil here, kind of on the ridge tops, and then down into the valleys and draws where the fire didn't burn as hot, and you can see vegetation still on the landscape. So here's an example of Overwatch imaging fire perimeters in action. So you're looking at a thermal composite image here. It's a mid-wave, long-wave composite image, so you can see background ambient temperatures, as well as a fire here burning quite strongly in an interface zone. So this is a result of the automated fire perimeter, where you can see a couple of spot fires at some distance away from the head, a couple of spots closer to the main body, and then a perimeter around the main body of the fire. Here's another example of that, just to kind of show it a little bit better in a grayscale image. But this is the result of the automated fire perimeter that we can produce. So that's happening in near real time on board aircraft. In this case, this is an initial attack fire. You have an air intelligence platform which is deployed to the scene, and within minutes you can quickly see the extent and the location and the mapping of the fires. Here's another example of that interface initial attack fire in Southern California. You arrive on scene, kind of seeing this aerial view, a couple plumes of smoke, and then in the infrared spectrum, we can see this small hot fire, which performs very well for a fire perimeter creation. So you can see in this case there was a initial spot fire, which likely escaped, some burning or and spread off towards the southeast of this image. So I'd like to kind of differentiate initial attack from late stage fires at this point. In this image here, you can see a forestry site which has a bunch of slash piles which are being burnt during a fuels project in the fall. In this stage of a fire, I think it wouldn't make sense to say, give me a fire perimeter here. You have kind of isolated heat sources which are geographically distinct, and there's probably a million ways for a computer vision application to draw a perimeter around these sources. But given that the fire hasn't moved between these sites, it really doesn't make sense to do that type of a problem. So in this case, you'd want to instruct the machine system to provide me a list of hotspot locations. And that's where I think the user community really needs to weigh in on this application, because the separation distance of hotspots, how should we group them together? If you're working on a hand crew and your job is to blackline within 100 feet, you may only want to know about certain size spots or spot fires that are distinct enough from their neighbors that you can go take action on it. And we can come up with a dozen different ways of producing a data product, which is lightweight and fast and easy to disseminate to crews' mobile devices, working in very bandwidth limited environments. We want to be able to distill this image, this 14-bit, radiometrically calibrated image, into a map that someone can quickly go take action on. So here's one example of that occurring. This is another fire, set of fires burn piles around a homeowner. This private landowner would assume that his home has been burnt up now because of this perimeter, but that's not the right way to approach the problem. So in terms of kind of spot fires and unburnt islands of fuel, when should those be included or excluded from an overall fire perimeter? We want to focus on tactical, real-time, operational data products, and interpretation as it sits today is currently like is art. You kind of know it when you see it, and there leaves a lot to the human expertise to interpret. But with the computer vision applications that I'll show in a second, we're approaching this from an automated point of view. So here's an example of a small, fast-moving fire. Again, kind of in the thermal, long wave, and mid-wave spectrum here. And how can we make an automated perimeter from this? So you'll see an arrow in the north. We have a spot fire. You'll also see unburnt pockets of fuel within the main body of the fire. So that perimeter can be delivered, air to ground in a couple of minutes, but the sensitivity or precision of which needs to be guided further by users in the field. I think there's an important trade-off here between precision and speed. So if this fire is moving at a very fast rate and spreading rapidly, if we were to wait a few minutes in order to process a higher precision of fire perimeter, that fire would then move and consume that fuel source and no longer be accurate. So I think that's kind of another area that incident commanders, division supervisors, researchers need to come together and define some of these terms as how tight would you like that fire to be wrapped up or shrink wrapped in this case. You know, this algorithm is a convex Hall optimization routine that can be tweaked based on the user's settings. And there's just a couple of examples of this. I'll move a little quickly now through the remainder just to give you guys an understanding of some imagery here. This is an example of categorizing and classifying heat sources using a computer vision technique. So looking for only the hottest parts of the fire. These intense heat polygons could be oriented to fire radiative power. When conditions on the ground exceed certain thresholds, the computer vision system can provide alerts to ground crews where rate of spread has exceeded a certain threshold or energy output has exceeded a certain threshold. Another example of that. So intense heat sources here being wrapped together, segmented and classified. Yet another example. So I also wanted to introduce this topic of constraining models kind of in a prior knowledge context. So fire perimeters, as we all know, never shrink or change. Once they are established, they only kind of add on from there. So we've developed a system which uses an existing fire perimeter and then builds off it from there. So if you have the ability to kind of observe a fire over a couple of different observational periods, you can use the model to expand the fire perimeter sequentially. So here's an example of an existing fire perimeter over this fire. That's yesterday's fire perimeter. You use that to constrain the model's growth and then come up with an answer which matches what our expectations would be. And then lastly, wanted to show an example of a fire progression model where you have the ability to observe the fire many times. So this is the red salmon fire from 2020. This fire kind of had the nightly observation pattern over a 60 to 70 day period. And you're able to kind of progressively increase the size of the perimeter using this routine. So I think in order to fulfill the promise of artificial intelligence, you need a couple of things to fall into place. You need a vision or a roadmap as to where we want to go. You need funding, you need technology, and I think we have a lot of those pieces in place. But having the definitions is so important because defining the data products that are the most useful to users in the field really isn't the role of scientists and engineers. And it needs to come from the firefighting community themselves. So I would like to kind of put out a call to action for everyone listening today that when firefighters start to dive into the world of remote sensing, that we need kind of algorithmic or quantifiable definitions. So how do we include islands and hotspots within a perimeter? What makes sense from a tactical perspective? If your job is to put out hotspots, you know, what is the size and separation and intensity of a hotspot? The data that we have access to today is so, you know, precise and high resolution versus what is typically thought of in satellite terms. And we have the, you know, opportunity to kind of take this a step further. And I would stress that it's important to kind of orient towards safety or tactical factors there. And it's equally important to have equal standards for all sensors. So, you know, whether you're looking at satellite data, full motion video gimbals, or kind of fixed cameras looking out at the horizon, we need a set of common standards here.
Well, thanks, Greg. There's two questions that I'm going to highlight here before we move on. One is from Eric Asselin. Would it be possible to change from speed to accuracy based on things like management action points, values at risk, or other priorities that may change over time?
Yeah, absolutely. I think the data processing capabilities on board the aircraft and payload provide you a great slider bar between kind of quick real-time information and more typical aerial survey methodology. Collect data, land, spend a couple of days doing orthorectification, aerial triangulation. If you want it to be very precise and kind of survey grade data, you can spend the time to do so, and kind of we operate anywhere along that slider.
Yeah, and thanks for that. And there was one other that I wanted to highlight from Dave Jones. How precise does a fire perimeter need to be when considering rainfall, debris flows, and mudslides? The fire could still be burning while heavy rain moves in on another part of the burn scar. Precise mapping of the burn scar could help save lives from a weather warning perspective.
Yeah, Dave, I think that's a great question.
The other thing I wanted to mention, there you may want to scan the chat there, Greg, if there's other ones that I missed, but I'd like to move on here to the next presentation. And thank you for your great presentation. There's
absolutely. Thanks everyone for your time.
If you can hang on and be on for the open-led discussion here after the next presentation, that'd be great because I have some questions and thoughts for you. I'm going to bring up Marcel La Riviera is a co-founder at Exospace, which seeks to expand space infrastructure through on-orbit data processing services. And while I'm setting up your presentation, would you like to add to that, Marcel?
Sure, yeah, my background is in mechanical engineering, specifically astronautical engineering, and Exospace is a relatively new company. We were founded in 2020, and we're currently based in Los Angeles.
And I'll advance your slides for you.
Okay. Yeah, so at Exospace, our goal is to provide low latency insight on Earth observational data. And we do this by processing images directly on the satellite itself. So I'd like to thank Everett for inviting me to this presentation. This is my first TFRSAC meeting, and has been great hearing all these presentations so far. So thank you. You can move on to the next slide. So today I want to cover sort of high level what our technology is capable of doing and how that can be used in fire detection. So I'll first go over some of the current methods used for large area fire detection, and then talk about how we can reduce the latency as well as reduce the costs by using machine learning. I'll then go over our service that we call the Feather Edge platform, and I'll talk briefly about combining satellite data with data from other ground sources, and then end on what are some of our next steps. Next slide, please. So I want to go over mainly the aerial solutions used currently for large area detection. I purposely did not include some of the ground solutions as they wouldn't be as good of a comparison to, say, satellite imagery. So for current solutions, and we've just covered that, but in the last slide by Overwatch, but we have the manned-unmanned aircraft. And these are great because you get the data essentially in real time. And you have the flexibility on when to sort of deploy these aircraft. So you can send one out during an active fire, but you could also proactively sweep an area that is at a high risk of a fire after a lightning storm or something like that. The major downside, though, is that it is a relatively expensive system to send those out. And because it is lower to the ground in terms of altitude, it takes a longer period of time to pass over sort of the same areas. Another widely used solution is NASA FIRMS, which takes in data from satellite instrument MODIS and VIIRS. And these are at about an orbit of 700 kilometers. So you have a good mix of high coverage and a good revisit rate. You can image the same location about 3 to 4 times in a 24-hour period. And the best part is that it's free. So that's good. The downside is that the ground sampling is fairly large, so it's difficult to pick up those smaller fires. And the 3-hour delay in latency would allow the fire to spread even more. So next is we have the commercial side, so the commercial satellites. And I'm talking specifically about the ones in low Earth orbit. So these are the smaller sort of CubeSat, smallsat range. And these are good because you can get the higher resolution. You can get 5 meters and below. And it's scalable. So meaning with each satellite you add to your constellation, the more revisit rates you can get. So I'll take California as an example. With one satellite operating about 500 kilometers, you'd get a revisit rate of 2 times per day and 2 times per night. But with 10 to 15 satellites, you can increase that to a revisit rate of once every hour. There is a caveat though, currently, commercial satellite imagery is expensive and the data is not coming in on time to be useful or to be used to its full advantage. So this is where artificial intelligence comes into play. If we're able to process data on the satellite itself, we not only get the benefits that satellite constellations provide, but also reduce the data latency and reduce the cost. So yeah, at aerospace, we're not trying to replace the current solutions, but to improve the use of satellite imagery for fire detection. Next slide, please. So what is data latency? Well, in today's context, that can be characterized as the time delayed between when an image is captured and when the useful data is sent to sort of the end user. So for satellites, there's 2 primary bottlenecks that cause a delay. The first is delay between when the image is taken and when the satellite passes over a ground station that it can downlink to. So this can range, of course, depending on where the image is being taken and where the ground station is, but generally it could be a few minutes to up to 30 minutes. The second delay is getting that data from the ground station to the end user. And Earth observation satellites downlink terabytes of data a day today, which is a lot of data to parse through, and usually gets sent to data centers before finally getting to the person that needs it the most. Then if you add some event detection model on top of that, like fire detection, it just increases the latency. And also the company analyzing the data might be different than the company capturing the image, which just keeps adding to sort of that latency. So how do we fix that? Well, our approach is processing the images directly on the satellite in real time. So on board, we would have a machine learning model that is trained to detect fires, and we can actually take advantage of that first delay. So while the satellite waits to get over a ground station, we've already processed the data. And then we can essentially eliminate that second delay since we only need to downlink the useful data, such as the image of the fire and the GPS coordinates of it. So by doing that, the data downlink footprint is actually a lot smaller, and it can be sent directly to the end user if there's a ground station nearby them. So with that, we've estimated that we can get the data latency down to about 30 minutes, and this is essentially the delay in getting to the ground station. If we were to say have an optical communication on our satellites, that would essentially reduce the latency dramatically. It'd be almost instantaneous that we could get the data down to the right person. Next slide, please. So the second issue with commercial satellites is the cost of the data, so which can prohibit organizations from even accessing, the wildfire data that they're looking for. And one thing I want to mention is the cost to send small satellites to orbit has gone down dramatically over the last few years. So we can get our data processing device to orbit in under $100,000, which is amazing. And then with an AI satellite, what's nice is that you only need to pay for the relevant data rather than all the raw images that you want of a certain area. And most of these images might not be useful. There might just be one that has a fire in it. Secondly, a fire detection model can replace some of the work done by analysts. So that's another way that cost can be saved. And thirdly, the same model can be used by various organizations in different regions. So a fire detection model that was trained to look for fires in California can also be tweaked to train to then look for fires in Western Canada or Australia. So you can have some sort of cost sharing for that as well. Next slide. So with that being said, we're planning to launch our FeatherEdge, what we call our FeatherEdge platform, to tackle these data latency and cost problems. Our first satellite will launch in October of 2022, and on board, we'll have access to a visible and near infrared camera with a ground sampling distance of 5 meters. So the FeatherEdge platform is a hardware-software solution that can run artificial intelligence and machine learning models in space. So the platform works by receiving images in real time directly from the onboard camera, and then running them through an advanced processor hosting trained AI ML models. And then the applications that are hosted on board can be uploaded to the platform and at any time, and can be updated any time during our planned 5-year mission. And the type of model that it supports is the widely used TensorFlow. So not only can we host sort of fire detection models, but we can also host models for, say, flood detection, vessel detection, just anything that sort of object classification detection that someone wants to do. Next slide. So now that we've detected fire, the next step is sort of to predict on how it'll spread and assess the risk of it spreading to certain areas. So we do that by providing a machine learning model with sort of the weather and soil conditions, fuels, historical data, etc., that can predict where the fire will spread to and assess what areas are most at risk and where efforts should be focused. So this info can be provided to the people actively fighting the fire. And as the fire is spreading, we'll get updated images from not only our satellite, but we can also get info from other sources, which will constantly update the model. Next slide, please. So what are our next steps as a company and with our platform? Well, we're looking to partner sort of with experts in the industry, such as yourselves, to combine our platform with a trained fire detection model. So we're looking to collaborate with organizations to create a fire detection model that can be uploaded to our satellite. And we also want to help combine our satellite data with data from other sources on the ground to create a more in-depth fire spread prediction model. So our goal is to learn as much as we can from the fire community. So yeah, please feel free to reach out, and would love to talk. Next slide. Yeah, so that's it for me. If there are any questions, I'm happy to answer them.
Thanks, Marcel. Yeah, I like your edge processing approach there with the small sats or micro. I don't know which class that falls into. But
yeah, you could say CubeSat, or we're specifically will be on a small sat, but yeah, it can be, our device can be on multiple size satellites.
Right. Let's see. Are there any questions in the? I don't see any there. But yeah, a couple things you touched on, being able to fuse data from different satellite systems in a sensor web type function. That's very valuable for lowering false alarm rates and improving positional accuracy when there's fire detects, or the positional accuracy for fire location, things like that. So
I'm seeing some questions on the chat. I can try and answer them.
Sure, go ahead.
I think one is how many platforms are initially planned. So first we have just the one that's sort of our testing platform, and we have one customer that's on there, but we would like to try and launch it, at least a satellite every quarter after that. So that's sort of the plan on that. One of our first customers is tracking shipping vessels to try and intercept illegal fishing, because they need fast data on that. So the specific processor we're using is not space qualified, so that has been one of the challenges, is to essentially mitigate against that. Some of the challenges is thermal and the radiation effects. So that's one of our proprietary things, is sort of the enclosure and the let's say software mitigations to be able to put a commercial off-the-shelf product in space to be able to process the data. One other question was to add different spectrums. Yes, that is something we're looking into. Currently, or the satellite we're on also has a multispectral camera as well that we will be hoping to tap into, but we're pushing our sort of satellite integrator to have other cameras on. All right, another one is, are you using or do you plan to use your algorithms on other OEM satellites too? Yeah, so our device will be available to other satellite as well, so they can purchase the device and be able to do the sort of same functionalities that we're planning to do.
Is there the possibility to add SWIR, middle wave IR, and thermal IR spectrums as opposed to VIS and near IR? There is a sensing gap in this space.
Yeah, like I said, yeah, we do plan to move into sort of those. We're a bit restricted on what our satellite integrator has on board in terms of cameras, but there is a multispectral camera, and we would like to move into SAR as well to be able to process images, SAR images.
Well, thank you, Marcel. I think we'll go ahead and move into our open-led discussion now, and yeah, I guess if the folks from the previous couple blocks here want make themselves available by video. I have some, let's see, I'm trying to remember who, I think it was, let me look at my notes here. Andre had the connection to the JAIC, the Joint Artificial Intelligence Center. And I had heard that they were interested in the wildfire mapping mission. And I think that they kind of concluded that effort. I'm not positive, but my understanding is that they had concluded that, but I didn't know where, where the outputs from that effort went.
Yeah, really great question. So yes, you're absolutely right. So JAIC, when we were working with JAIC, they really had their humanitarian assistance disaster response mission. There's been some kind of organizational shifts there and shifts in priorities for where that work is going. So yeah, right now JAIC is not really interested in continuing in on the wildfire work. So right now all the tools, capabilities, codes here live at PNNL through a cloud system on Azure. So with the kind of ramp down of the fire year, we've put the system, we've suspended the system right now just to save on some costs. But we are working with some other entities maybe to think about moving this capability elsewhere. And with that, the role really of a national lab is to focus on fundamental science and applied science. And so, we've done a lot of the R&D here. Our role really isn't necessarily to take the system and run it in the long term operationally. So what we've developed right now is an operational prototype. It functioned over the summer months through to the fall, really monitoring every imaging and providing analytics on every fire within CONUS and Alaska. So right now, yeah, we're a little bit maybe in a holding pattern, in terms of where this goes next.
Yeah, and thanks for that, Andre. And I'm kind of hoping that this meeting here, bringing people together, talking about different niche applications for artificial intelligence and machine learning in the fire mapping, fire suppression, fire detection realm. I'm hoping that we can get a clearer picture of what we need to do, what some of our potential hurdles are in terms of getting to a point where, let me give you an example. Today we've heard talks about smoke detection, using the scanning cameras to look for smoke or fire. And let's see, Greg talked a little bit about the actual vector fire mapping piece where you have an image of a fire and you're drawing polygons, points, lines, and polygons. That particular application of looking at a thermal image and drawing points, lines, and polygons is a very keen interest point to me. I don't know if Jan Johnson is online, but you know, Jan, we have a host of people that are trained infrared interpreters, and their job is basically to take thermal imagery and draw the points, lines, and polygons. You know, and they go through a training process where they're trained in how to do it. Every person that draws a fire map is going to draw it a little bit differently, so there's some subjectivity involved. And you know, like Greg said, you know, are you lumping or are you splitting here? Do you leave these as 5 separate spots, or do you group them together as a single one? And I say that that's the art in the art and science of drawing fire maps. Now, the thing about that is you know, drawing these vector maps that are provided to the GIS teams that provide maps to the incidents. There's a level of latency that's there as the folks are examining their images and drawing their lines. And there's also a cost there of having these people spending time drawing the maps. We also have this for some of our products like FireGuard, which is a product produced by the National Guard. Their product is going out every 15 minutes, and it's going to be changing to every 10 minutes. And those polygons can be a little bit more crude. And I think, you know, based on the timing, you know, getting something out every 15 minutes or every 10 minutes, but by nature, you're going to have to be a little bit more crude in your drawing of the polygons. But anything we can do to introduce some automation to these processes where we can start to mimic what the infrared interpreters are doing will help to reduce our reliance on manpower. It should help reduce the costs, although I think the jury is still out on that in terms of, you know, what the real cost will be for using artificial intelligence and machine learning, and how well those algorithms will work as you move from one landscape to a different one in a different region, let's say. So one of my primary buckets of interest is the fire mapping piece, and so that's, you know, that's one of the things that I've been paying attention to key spots in our presentations over the last couple of days.
Everett, can I chime in a little bit on that?
Absolutely. I kind of ran out of air there, so go ahead.
There is a relationship between the need for speed and the need for precision. They kind of trade off.
Right.
In reality, the faster stuff can be crude. After all, it's going to be different in 30 seconds. So
right.
Being tied up by precision for your fast product is a mistake. And on the other hand, you know, the reality of fire perimeters is that it's actually a political thing. It's, you know, I've been doing this for 20 odd years, and the precision can sometimes be incredibly fine. It has to do with whether or not a house gets compensated that had some fire damage, gets insurance compensation. Is it in or outside the perimeter? Those kinds of questions have come up, and that's where the precision is required, but that is way after the fact. So there's a nice balance between, you know, my advice, Greg, is kick it out the door, and then give people the slider.
Right.
To that kind of approach is really the appropriate one, because that's the way the need works.
Right, and I'll use FireGuard as an example. FireGuard is intended to be a very early indication to the first responders on the ground where the fire is and how it's behaving. So you have these fairly rapid time slices. Let's say we go to every 10 minutes, so you get 6 of these time slices an hour. So you're kicking out these somewhat crude polygons. From those polygons, and with that degree of frequency, you're able to start getting a feeling for the direction of spread and the rate of spread. And that's really important in these dynamic fires that pop up when you have high winds and dry fuels and populations at risk. And so the precision in those cases is not that critical. It's not as critical. You want to have a general idea of where the fire is, but really the key bits are what direction is the fire moving and how fast is it moving in those directions, so that they can deploy resources and also get people out of harm's way, call the evacuation orders, move the evacuations in a way that's moving away from the fire instead of into the fire. So, I think the Firehawk or the Fire Guard is a good example of where that sort of automation help would be really useful. And we have lots of data to work with, and it's my understanding that with artificial intelligence and machine learning, that the more data that you have, and having a refined idea of what it is that you're trying to do, mimicking a human process, that you have a chance of some success at doing that.
Yeah, I think I'd just jump in here and add that, if we're asking for what is the correct answer, what is the correct definition, we're probably missing the point that, we don't want to be too prescriptive, from a research and academic perspective. That I think our goal is to be more supportive of the firefighter, and that there probably isn't one best answer, that there are probably many, many good answers, and kind of supporting the firefighter with the ability to make those decisions on the fly, take advantage of their expertise, provide a supervised classification environment, a supervised output, so that they can really tweak it and take a hold of it, make it their own, and then take these tools out into the field.
You got to remember that not a single perimeter is absolutely correct, right? Perfect is the enemy of good. Really is really appropriate. You can have drawn the best thing you possibly can, but it's not that precise.
I think Tim Chavez might be online. Tim, I'm sure you have some perspectives on this as well. So if you have some thoughts where you'd like to join in there, please do so. Did I interrupt someone that was getting ready to speak there?
Yeah,
well,
so sorry.
Go ahead, Angel.
No, I was just gonna say that as Ever noticed, I think it's also really important the temporal part of it. So not only having a picture at the time and at the moment, also knowing how it's progressing from a previous time. Also, not only for risk assessment, also for knowing how to also initialize and assimilate models that can actually forecast later times. So I think that's also a really key point on also not having only a single picture, having a progression.
Yeah, and that's actually my second bin, and thank you for putting that out there. Is that the fire mapping piece is one bin that I have. The other one that I have immediately is the fire predictive behavior modeling, and we have fire predictive behavior models, and it's sort of this Monte Carlo simulation where, as you go further out in time, the models may start to fall apart a little bit because your estimation of the variables is maybe a little bit coarse. Fire has a couple different pieces that really impact how the fire behaves, where it moves. One is the terrain, one is the fuels, and the other is the weather. And so we have varying handles on those different variables. The terrain is pretty simple. It's there, it's not changing. The weather's changing, the wind direction, the humidities. And then the fuels, they're quite variable over small spaces and extents. And actually the physics of fire and the physics of burning is, it's a pretty complex problem. So trying to work all of those things together, and I think that if we can take fires that have already happened and look forensically at them, if we have high frequency of time slices on those fires, we can see what actually happened on those fires. And then we can start to dig down into things like, well, what was the weather doing? What were the fuel types, and so forth. that influence these fires, and then we can start to play around with the modeling to see which approach gives us the most accurate prediction on how that fire behaved over that period of time. Once you have that point of ignition, then it starts to spread out from there, and then it falls into the influence of those three factors that I mentioned.
And not only external factors, also the fire it's changing those factors at the same time.
Right. The fire generates its own weather, and
so yeah, that's also another important part of it, is that you need to actually spin up what the fire is doing for a little bit of time, and then you are creating its own weather and its own conditions, and then you can start forecasting properly the fire.
So Angel, you must have worked with Janice Cohen on the fire atmosphere coupling.
So we have our WRF Fire, which we collaborate with CU Denver, John Mandel, and also we have been also running it here in San Jose State University, and we are maintaining this community code, which is a fire atmosphere couple model, WRF Fire, which is it's inside WRF. And there are a couple of other, there is an NCAR group that is also maintaining it as WRFire. But everything boils down to the same core component, which is running fire prediction inside WRF, community weather model.
Right. Yeah, that's a really good point.
So I was just going to jump in here, because I feel like there's a couple places where we can make some advancements in all this, and I love WRF S-Fire and its capability. But one of that is on the fuels inputs, and so I think with a lot of the sensing capabilities that we have now, we can do a better job of getting just in time inputs for things like WRF S-Fire. And that's everything from vegetation moisture index to soil moisture to using, I mentioned in my presentation, the JEDI sensor, where we can, use LiDAR, understand, bulk density through the column, understand where you have those high density of ground fuels versus more in the ground. So I think that those are important to think about. The other part is feedback loops in between this, and so where you can couple observation, sensing, feed that back into WRF S-Fire, and do restarts on those models. This is my current system state. Let's forecast out from this point forward, just to try to keep the keep things constrained.
Yeah, and it's Tim may be able to back me up on this, but my feeling is that if we can improve the fire behavior models and produce more rapid turnaround on those can also be very useful to the incident commands when they're planning their strategy for the next 6, 12, 24 hours.
One of the is Tim Chavez on?
He just posted a comment there that he said there is some really important work being done by several using real-time fire progression observation to tweak fire spread prediction models and even observe wind speed caused by the fire.
So one of the other things, and this actually something that Tim and I have talked about a lot, is flame length. He's a fire behavior analyst, so one of his jobs is to kind of get a handle on what the flame length is today and what it's going to be tomorrow, because that has a real impact on the way that assets are allocated around a fire. You don't put a hand crew in front of a 10-foot flame length fire. So he's got to look forward to what the possibilities are for tools to fight the fire the following day. And the best way to do it, what he does is he walks around out on the fire and looks at the flame length and says, okay, I'm going to have this kind of flame length and this kind of fuel tomorrow, given the weather forecast. So one of the things to sense, and that's one of the reasons that I've got that 8 filter camera system is to look at flame length. That is an operationally important parameter.
I'm taking
and
notes
it is
here.
and it is for the models too. Frankly, that's it's important in both cases. So
agree with you 100%, Tim. And like I said, using the feedback and fire behavior prediction is going to become an iterative process where you observe the fire, you make a prediction, you see what actually happened, you re-enter your prediction with the adjustments that you observe, and that can happen multiple places. Multiple places around the fire, multiple times a day. That's the future.
Yeah.
It sounds like your dog. It sounds like your dog was just agreeing with you there. So, let's see. Jack Gill says, my team and I from Purdue are hoping to develop a solution to better collect and categorize ground fire fuel data. Stay tuned for our presentation later today. And Elise Bowen, who's a infrared interpreter, sounds like what the fire behavior analysts already do. So, any other comments from the assembled group here? This has been a great break from the PowerPoints, and I think a nice sort of wrap to the artificial intelligence machine learning piece. So if you have any closing comments.
Hey, Everett, this is Monica Coakley from Lincoln Laboratory. Even though it's not machine learning, we've been thinking about, weatherfront algorithms and applying that to the high resolution temporal data, but coarse resolution data. And you were talking earlier about, just the perimeter and the importance of the perimeter and how it might be less, lower quality if you had high temporal update. We're always interested in the data to actually validate that. And, it seems to me that in general, one would want to know the quality of the data. So if you did have something that was a degraded perimeter, there should be some quality metrics on it in terms of how good is it? Because I think that's useful to people as well.
Yep, that's exactly right. Thanks, Monica.
And we're definitely interested in high resolution data. So if there's someone has high resolution data, I got a link from Neil earlier. But if there's other high resolution data that can be used to validate, say in the case of the Dixie fire, I know we'd be interested in that.
Thank you, Monica. Let's see, I did want to read a comment from Deepak. It would be good to study and correlate flame length versus convective cloud height, since the latter is always a good energy metric.
That's one of the things that's going to happen in those burns in the southeast this spring. Craig's coming down with the LiDAR and radars, and I'm going to be flying each one of those. Well, the things at Fort Stewart, there's 4 burn plots at Fort Stewart, and there's about 60 smaller things in Florida around Tall Timbers, and we're going to be collecting data on all of those.
And that's great, Clement.
Right?
Say again?
This will be the FASME experiments.
It's FASME and CERTUP. Makes everybody's cooperating on those burns.
Good, thanks for that.
Let's see, Mike Pavlonis from NOAA says, who spoke yesterday, said, like other aspects of the fire problem, behavior forecasting has not yet found an operational home where the forecasts are routinely generated in a sustained manner. The models also depend on some non-operational sustained 24/7 observations. Dr. Seaton from University of Illinois Chicago says fire prediction software should get real-time video feed from cameras and other sensors. And Dee followed up by saying, I know NASA had studied this in their instrumental biomass burning in the African safari campaign. And Peter asked, can someone contact me about the FASME experiments? And Peter, I'll be happy to make those connections for you. So I guess we're slightly behind schedule, not terribly so, but we're on the verge of a break here. Is there any closing comments that anyone would like to put out there to sort of wrap this up? If not, we'll go ahead and cycle to the break. And during the break here, I wanted to give Dave Jones an opportunity to show off the GeoCollaborate capability. So I'm going to stop sharing here. And Dave, if you're out there, let's see. For the break, we had a 25-minute break scheduled. Are you there, Dave?
I'm here. Can you hear me okay?
Yes.
Okay, great. Yeah, I just however much time you have, I just thought this would be a little fun overview and demonstration since I've showed GeoCollaborate in the past, TFRSACs, just to give everybody an update and to show people who may not have seen it what it can do.
Sure. I think if we got people back at 3:10, that would put us about 5 minutes behind schedule, which is not bad at all. And that should give you some ample time here to during the break here to show your GeoCollaborate capability. So if you want to share your screens there,
okay.
And we'll have this as sort of a rolling break here where, folks can get up and get their lunch or bio breaks or whatever they need.
Okay, let me just verify that you'll be able to see my my screen here.
Let me go ahead and close my camera off
here. This one. Can you see that screen?
Yep.
Okay. This is just I'm Dave Jones with Storm Center Communications. We developed a technology under the SBIR program, Small Business Innovation Research, called GeoCollaborate. This was one of the slides I showed at the last TFRSAC meeting, and it looks like it's a little bit messed up at the bottom, but I just grabbed it from the previous presentation, where we use GeoCollaborate to support the California Civil Air Patrol to coordinate with the California National Guard on the August complex wildfire, so they could see disparate data sets on a collaborative common operating picture, so they could do some coordination as to when the Civil Air Patrol could swoop in and take these images, as many as possible. These yellow boxes that you see are task orders for imaging where structures were that the California National Guard wanted imaged. And the color that you see on here is the high resolution rapid refresh smoke model, the HER smoke model, or a smoke output from the HER model from NOAA, which was operational. So this was a forecast of 6 hours in advance when the smoke would clear, so the Civil Air Patrol could get in there and take some images. So I just wanted to give you an overview quickly, because it's really important that the Small Business Innovation Research Program get the love that it deserves and the awareness from agencies within the federal government. And a lot of people have told me in the past, and when I meet with them, that they're fully aware of SBIR, but they're aware of it from the standpoint of funding SBIR Phase 1 projects. A lot of agency people and staff are unaware of the value that a Phase 3 SBIR brings to the table. So we developed GeoCollaborate under this SBIR program. We've gone through all of the phases, and we are now a Phase 3 technology. And GeoCollaborate is basically a new capability that enables active collaboration. It's not screen sharing, it's actual geospatial data sharing across platforms. And we call it a capability that enables unification of trusted data. So once you've identified trusted data sources, you can bring them in and just make them on-off switches and share that data out in real time for people who are on other devices or in other locations, which really pulls together real-time decision-making environment. The easy-to-use interface has evolved over the last 6 years. It takes a long time to make an easy-to-use interface, and it works across platforms on any device. So the big thing that we usually have to stress when we talk about GeoCollaborate is that it's not a technology that comes out to replace anybody's portals or websites. It actually relies on those portals and websites to be a trusted data feed. GeoCollaborate is you can think of as the collaborative plumbing that can connect any system in a real-time environment. So any data that's collected and wants to be shared can be shared. And I'll show you that. As a matter of fact, I'm going to send a URL out in the chat just for fun. So I'll do some collaboration and you can connect and participate in real time. So this is what SBIR is. It's the federal government's multi-billion-dollar seed investment fund in small business innovation. We answered a grand challenge in 2011 from NASA, and that challenge was how can agencies access and share their data? So we were funded in 2013 for phase 2 to develop the technology. The federal government did a deep dive and found the technology to be not only unique, but profoundly valuable to the federal government. And then we were funded in 2015 under phase 2E to extend the collaborative capability to all mobile devices. And then later in 2015, we were issued a phase 3 contract from NOAA. We now have 4 contracts, sole source contracts with NOAA to utilize GeoCollaborate in different areas. One is with the JPSS program to put more NOAA satellite data to work in decision-making environments. One is with the Hurricane Research Division. They want to put GeoCollaborate in the Hurricane Hunter aircraft so they can share data across aircraft, and also with scientists on the ground. Another is with the National Weather Service, the National Water Center. So we can, they're using GeoCollaborate to have exercises with states around the country. Other agencies that are using it, DHS CISA and the Census Bureau and the All Hazards Consortium. But the really significant thing about the phase 3 status is that the technology can be acquired on a sole source basis with any federal agency. It cuts across civil, intelligence, and DoD. And there's no ceiling and no time limit to any contract that's issued. And phase 3 companies can have partners to bring to the table to help the government achieve its requirements. So it's a very powerful status in the SBIR world. So I just wanted to show you this before we dive into the real-time collaboration. You may have participated in briefings like this where the person giving the briefing opens up a lot of web browsers, and you might see, that they're just paging through maybe 20 or 30 or 50 web tabs to go through it. What GeoCollaborate does is it pulls out the trusted data from those websites, hubs, and portals and puts them into a collaborative common operating picture that anyone can connect to using a URL. And so what you see here pictured, like the red states were states that issued declared states of emergency. The blue dots were COVID counts, USGS real-time earthquakes coming in, the National Weather Service's watches, warnings, and advisories, and the state of Pennsylvania. These green dots were what rest stops were open for truckers to stop. This was at the beginning of COVID. And so this is, from an interface standpoint, is what it looks like. You have a leader that logs in with credentials. And then you have an unlimited number of followers that can follow in real time as the leader is moving the map around and accessing and displaying trusted data sources. We heard so many awesome presentations earlier today and yesterday, people generating data sets. Think of any of those data sets being available in real time, whether you want to advance research, whether you want to advance situational awareness and decision making, or you're just playing with some prototype products and you want to get feedback from people in the field. All they have to do is connect to a URL, turn it on, and get exposed to what it is you want to show. And then you have a collaborative dashboard at the bottom. This collaborative dashboard has all the data layers that the leader shares, and the user of the dashboard, which also there's an unlimited number of users for the dashboard, they can zoom in and around their area of interest. So you see some weather service advisories issued here and fire perimeters from NIFC. that are updated all the time. And the thing is, any OGC compliant data formats can be used for rapid interoperability. There are ones we're funded under an OGC disasters pilot currently, looking at different evolving formats that OGC is bringing to the table. But satellite data, drone output, models, observations, reports, pictures, outputs from automated intelligence or machine learning, all that can drive data-driven decision making is something that we can bring to the table. So why would you use GeoCollaborate for wildfires? Well, first of all, you can have an active collaborative session where you're connecting perhaps NOAA with the IMETs in the field and then briefing firefighters, or to do any sort of coordination, verifying, validating data, identifying gaps in observation networks, just fostering this new collaborative research approach. Cross-agency coordination is, I've been hearing this for more than a decade. Agencies have to work better together. They need to be on the same map. They need to be this and that. And now we have a technology that is a phase 3 SBIR that is ready to be put to work. Response activities, enabling coordinated response to events, improving situational awareness, verifying reports and observations. And then under communication, really providing a user-friendly interface. There's media-ready graphics, so you can go into a full page mode where you're just showing some of the data that you can use for media briefings. And then if the media connected, they could take that directly on the air as well, or just shoot it with their camera. The delivery of key points and the key points window also alerts people maybe when the next briefing is coming up, what's the next meeting. You can put links in there for a Zoom or a Google Meet or a Teams meeting as well. So what I'm going to do now, I'm going to split my screen in two, figuratively. I'm going to put an address in the chat. I'm going to have to get out of this. On the left-hand side is going to be the leader, and on the right-hand side is going to be the follower. So those of you who don't want to click on the link and open up a browser and turn it on and follow and stuff, you don't have to do that. This is just for a little bit of fun. So I'm going to get out of this here, and then I'm going to go to my bring up my split screen. So on the left-hand side, and let me see if I can. I don't know if I can go into, I'm using the web version of Teams, and I'm not sure if I can access the chat. Let me see if I can. Hold on a second. I don't know if I can or not. I see that Teams is doing my screen sharing, but I don't know if I can use the chat. So here's what you can do. If you would like to connect to the link, connect to this link up here. It's FS for Fire and Smoke. We're funded under NOAA's JPSS program under their Fire and Smoke initiative. fs.geocollaborate.com/follow. And when you connect to this address, this map should come up. So I'm not going to ask for feedback. I'm just going to assume if you want to connect, you can connect. And let me just say a few words about this quickly. I've logged in as a leader on the left-hand side, and I have added some data sets in there. On the right-hand side is the follower. This is a simple web map. You can move around, zoom in, zoom out, do whatever you want. But as soon as you turn GeoCollaborate on, once you click the on switch, then your map is going to match my map as the leader. Now you'll have a little wider domain because I've split my screen in half. So you'll see more of the map, but essentially now I have control of your map. I can zoom right in. Let's say this is the perimeter. This is the wildfire perimeter for the Dixie Fire. You can see that data set has been shared across all the web maps, and you as a follower can also interact with that web map as well. And I can zoom out here. You'll see some data from NASA firms. This is the Motus fire. This is current today, where you can link to more NASA data sources. But these are hotspots identified by Motus and also identified by VIIRS. That'll come in when you'll see just VIIRS up here if it's a VIIRS fire point. And then you'll see all of the fire perimeters from 2021. Now, you as a follower can also change your base map. You can click this arrow on the left-hand side and you can